Okay. Good evening to everybody. A very good evening to each and everyone, dear students. Can you able to hear me? Please raise your hands. Yeah, is it okay? My voice is clear for you? Right. Fine, fine. Yeah. Very good evening. Very good evening to each and everyone. Yeah, the people are I was already joined, but waiting for the people. Okay, I hope so. All of you have joined, seems. Yeah. First, let me introduce myself. First of all, I hope all of you are fine during this pandemic situation, right? So, since past 1.5 year onwards, we are facing the problems with this COVID and attending the online classes. The education system has been changed. Most of the education is shifted to online mode. I hope this is also new experience for the students as well as for the faculty members. But of course, one way it is having its own advantages and disadvantages. But we need to think about only advantages, correct? And whatever we have chosen means don't think any disadvantages. So yeah, this is also best mode. Saving time, sitting at home. Fine? Yes. Yeah. By the way, I am Dr. N. Mallareddy from ACE Engineering Academy. My qualifications, basically I am diploma man, Polytechnic from Mahbub Nagar Government Polytechnic College. After that, I did my BTech from Sri Venkateswara University, Tirupati. Later, I completed my MTech from JNTU Hyderabad with a specialization of power electronics and electrical drives. PhD is also from same university, JNTU Hyderabad, in the area of unit commitment problem. Unit commitment problem, that is startup and shutdown schedule of the synchronous generator. Unit commitment means it is a startup and shutdown schedule of the synchronous generator to meet the forecasted loads on the economical way. And in other words, unit commitment means how to the connected alternators in parallel and how to shift the load on the alternator, load sharing of the alternator, and everything is based on the economical way. It is mostly so during parallel operation, right? What set of alternator has to be switched off and what set of alternator has to be switched on to meet the forecasted loads on the economical way. That is my PhD. It's nothing but mostly parallel operation of alternators and load sharing. Now, I have 20 years of teaching experience for engineering education and also 7 years of research experience as well. I published 15 papers in national and international journals and authored 2 textbooks. I wrote 2 textbooks, but not on the machines. So on the MTech, my specialization is MTech, and based on that, so I did some research, and based on that, I authored 2 textbooks. Now, presently, I am working as professor and head of the department in G. Narayanamma Institute of Technology and Science. That's for Women's College, Engineering College, one of the its most popular college in Hyderabad. There, I am working as professor and head. My association with ACE Engineering Academy, since 2004 onwards, imparting gate coaching and also coaching for engineering services examination and all public service examinations, undertaking examinations, right? And all state government examinations and all other competitive examinations. Yeah. So this is my background. And I am going to handle the subject called namely synchronous machines. Fine. And as you know, the machines can be divided mainly into three parts: DC machine, induction machine, and synchronous machine. DC, induction, synchronous. In DC machine, DC generators and DC motors. Induction machines, it is transformers and induction motors. Synchronous machines, synchronous generators and synchronous motor, some special motors also, like reluctance motors, and the stepper motors. For ESC students, it is also there, the stepper motors also in your curriculum. Fine. But among these three parts, DC, induction, and synchronous machines is giving almost equal importance for gate coaching, gate examination, and ESC examinations, right? Yeah. In gate examination, almost for these three machines, total machines part 12 plus, nearly 15 marks you can expect among all these portions. Okay. Yeah. He is giving almost equal importance. But being the students, they will feel synchronous machines as a bit tough compared with all other machines. Of course, reasons may be some XYZ. I can say the main reason is there is no proper preparation. While being the students, to DC machines, if you take, it will be in the second year level, second year or first semester wise say. The first part is DC machines, no? Yes, second year level. At that time, students are juniors, more interest on the studies, right? You will pay more attention, and whatever the faculty, so the work is being given, you used to do it, you can enjoy, and subject is also comparatively simple. Fine, yes. But coming to the next semester, the next part is AC machines is going to be started. Okay? That induction machines and transformers say. But at that time, you are in second year, second semester level. But last part of synchronous machine is in the third year level. At that time, students are seniors, and your activities, you will have many activities. Your concentration may be deviated in different ways, right? At the same time, subject to complexity is going to be increased, correct? From first year to final year, year to year, so complexity is more. But at the same time, students will not focus that much. Interest is going to be reduced, correct? So interest, subject's complexity increases, interest decreases. If you draw the interest versus time, interest on y-axis, time on x-axis, so like first year, second year, third year, final year, interest, first year, second year, third year, final year, and y-axis interest, say, if you draw that, interest will reduces exponentially, exponential decay. Correct? Yes. Interest is reduced. That's the reason you might have not concentrated, focused on the subjects. That's the reason you may be feeling a bit tough, but not like that. Once you are synchronized with synchronous machine, they are far easy compared with all other machines. Because DC generator and synchronous generator working principle is same. Okay. Only difference is synchronous machines. Synchronous machines is a part of the power system. Most of the power generation is by the synchronous generators. So it is connected to the busbar power system. Power system is nothing but generation, transmission, distribution. Generation, transmission, distribution. So generation side, most of the power generation is synchronous generators. Therefore, connecting the synchronous generators to the grid, synchronization methods, and stability of the synchronous machine, parallel operation of the synchronous machine, how load can be controlled, how active power can be controlled, reactive power can be controlled. At the same time, you have to maintain the stability. With respect to all these points, this point of view, synchronous machines will be involved lot more concept. Fine. But nothing to worry, nothing to worry. I'm here to clarify or to make this subject as simple as possible so that everyone can able to attempt all the questions. I'm sure that at the end you are going to experience the same thing after completion of the topic, our synchronous machines. So everyone can able to complete. But only thing is you should be regular to the classes. Correct continuity has to be maintained. As you know, machines topic or every electrical engineering subjects continuity topic to topic continuity will be maintained. So for example, if one class is absent, say if you attend the next class, then gap will come. No? Yes. So due to any reason, if you miss that class, what you have to do? For coming to the next class, what was happened in the last class, so that you will be in touch with that topic. Okay? Yes. And from your cooperation is compulsory needed. Yeah. And before going to start our subject, synchronous machines, let us see, this is the syllabus for ESE examination and also the ESE and GATE examinations. Syllabus is almost same. GATE or ESE subject is same. Na? Only extra topics may be added. Extra topic means some special motors may be added. You can find the syllabus for ESE, performance, right? The regulation and a parallel operation of generators, motor starting, characteristics and applications, servo and stepper motor. So this topic only extra for ESE people, servo motor and stepper motors, right? It is not there in the GATE examination syllabus. Okay. Otherwise, the syllabus is almost the same. So here, in this batch, GATE students are there, ESE students are there, okay, and any other. So some students might be joined to learn the subject or for to write the state government examination, whatever it may be. First, we will complete our syllabus, which is suitable for all competitive examinations. All competitive examinations, because having more than 17 years of experience in this only GATE coaching. I have joined in AS in 2004. So nearly having more than 16, 17 years of the GATE coaching experience, we have seen all examinations, seen all ESE, GATE and IAS examinations, all competitive examinations, and we know that how to handle. Fine? Yes. So it will be suitable for any kind of examinations. And coming to ESE examinations, the as you know, the type of question paper pattern is different. So you might have completed most of the machines. I don't want to go in detail about the pattern of examinations, unnecessarily boring you people. You may be knowing. Fine. Only thing is ESE examinations. So a lot more derivations, all those things will be there. That we will do at the time of mains examination. For prelims, all those things are not required. No? At the time of main examinations, we will derive all derivations. But during our class, some important derivations which is required to understand the concepts, definitely I am going to derive. Okay. Yeah. And only thing is, see, the GATE examination and ESE examination. Comparatively, GATE examination a bit tough. Prelims, if you compare prelims, ESE examinations and GATE examinations is mostly numericals. Of course. And last year onwards, he has used MSQs, multiple select questions also. That will be based on the concepts. 4 options you should know. 4 options may be correct or some may be correct. Like that. Fine. So GATE examination is mostly numericals. Getting good rank in GATE examination is practicing the problems. Keep on practicing the problems. Okay. Yeah. I am going to do the problems topic wise, the required problems suitable for GATE examination. And of course, at the same time, ESE examinations, right? In addition to that, you need to do 1 or 2 more problems. For each model, 1 problem. Minimum 1, maximum 2. Don't do unnecessarily extra problems. Okay. Yeah. And now, then coming to, this is the synchronous machines topic. The synchronous machines syllabus, I am going to divide into 8 chapters. The 8th chapter is only exclusively for, 8th chapter is only for the ESC people. And 7 chapters are common for GATE and ESC examinations. The first one, introduction of synchronous machines. Introduction of synchronous machines, right? There we are going to see what are the advantages of the synchronous generator over induction generator. What is the importance of synchronous generator, right? And EMF equation, frequency, and phase sequence of synchronous generator. What is the importance of all those things? Very basics we are going to see in the first chapter. And second chapter, construction of synchronous machines. In construction of synchronous machines, as you know, there are 2 types of synchronous generators, synchronous motors: salient pole synchronous machine and cylindrical rotor synchronous machine. So second chapter, it is including with construction of alternators. And third one, construction of alternator means even armature winding also. It is a part of the armature construction. Armature winding, short pitch winding, distributed winding, etc. All those things we are going to see in the second chapter. Third chapter, rotating magnetic field and armature reaction. Rotating magnetic field and armature reaction. Fourth one is voltage regulation and 2 reaction theory. Voltage regulation and 2 reaction theory. Various regulation methods: synchronous impedance method, MMF method, ASA method, ZPF method, all the regulation methods we are going to see. And 2 reaction theory. 2 reaction theory for salient pole synchronous machines. It is required slip test and measurement of XD and XQ. Problems on the 2 reaction theory. It will be added in the unit 4, 4th chapter. And next, power flow equation. The power flow equation, active power equation and reactive power equation, cylindrical rotor synchronous machine and the salient pole synchronous machine. The power flow equations are different. No? Yes, power flow equations are different, and based on that, problems, numericals problems based on that equations. 6th one is parallel operation of alternators. It's a very important topic. Parallel operation of alternator. Mainly in that we are going to see 2 cases: 2 alternators in parallel, minimum number of alternators in parallel, and alternator connected in infinite bus bar. Alternator connected with infinite bus bar. The synchronous motors, 7th chapter is synchronous motors. There we are going to see what are the various starting methods of synchronous motors. Okay. And stepper motors, this is only for ESC exams. This is for only ESC exams. Fine? Yeah. Now, and coming to textbooks. What are the various type of textbooks we have to use? So many textbooks are available. For machines means very old subject. Now it is not just now introduced to the subject. So it's having the hundreds of long back onwards. These subjects are there. So many textbooks are available. But we need to follow some standard textbooks. Standard textbooks. See, this is electrical machines. The electrical machines by P.S. Bimra. This is first one, is best book. Electrical Machinery by P.S. Bimra. And Nagaratan Kotari. That is Nagaratan Kotari is also good. And this is first book. This is second book. Please correct it. Electrical Machinery is volume 1. P.S. Bimra, Electrical Machinery, standard textbooks. It is quality wise and quantity wise better suitable for GATE examinations. Okay. So being the electrical engineering students, you should have this textbook, Electrical Machinery by P.S. Bimra, first one. And generalized theory of electrical machine. The second one, whatever I am writing, generalized theory of electrical machines. There, some important topic, transient operation and parallel operation of alternators, two reaction theory. That some topics will be is explained beautifully, and even stepper motors. Not only that, all single phase induction motors, etc. It will be given in the second textbook. Okay, this is third one. Nagarthan Kotari. Fitzgerald and Kingsley, that is okay. You purchase PS Bimra one. And also these textbooks also. Textbooks for your reference. The Ashfakusen, Electrical Machines by Ashfakusen, and H. Cotton, Electrical Technology, Alexander L. Dorff, M.G. Say, J.B. Gupta. The J.B. Gupta is also better for problems. For problems. Good for problems. Yes, because he has solved so many problems and many competitive examination problems also worked out examples are there. And all the solutions are being given correct because it is very old textbooks. So there is no mistake. Right? And you can also purchase this book also. Okay. All the topics are given clearly. For the learners, it will be good. And anyhow, you nothing to worry. At least you have one textbooks for your reference. And in my classes, regular classes, we are going to see each and everything. I will give the conclusions of so many textbooks and having my own conclusions, having so this rich experience. That notes is more than sufficient for you. I am saying more notes are more than sufficient, but one textbooks must be available so that you can do some new problems. At least some example problems, work out example problems. You can pick up some more problems, right? So otherwise, we are going to discuss in detail, nothing to worry. And coming to the weightage for synchronous machines. Weightage is for gate examination, as I told, 12 plus marks. 12 plus means mostly it will be 15 to 15 marks nearly. You can find 15 marks roughly for all the machines. Almost for each machines means DC, induction, synchronous machines. But induction you can again divide into two parts, transformers and induction motors. Like 4 parts we can treat. Like 15 marks means nearly each subject 4 marks. Sometimes it may vary. Like synchronous machines also, nearly you can expect for synchronous machines. For synchronous machines, 4 to 5 marks. That was I have given here. Please just see. 2017 examination. I hope you can able to see now. Yes, 2017 examination. There are 2 sets at that time. It was introduced 2 sets. Set 1 and set 2. 1 mark question is 1. 2 mark questions is 1. Okay. How many marks? 3 marks total. 3 marks. 1 marks and 2 marks is 1 question. 3 marks. Set 2. 1 mark question is 1 and 2 mark question is 3. How many marks? Here it is 3 marks, but here it is 4 marks. 4 marks in set 2. In 2018 examination, of course, you can get only for 1 question. But 2019, so this is 1 mark question is 1, 2 mark question is 1. So how many it will be? 3 marks. Okay. And 2020, it is again 3 marks. Fine. It may be 3 to 4 marks we can expect. As I told, nearly, roughly 4 marks. Worst, if it is very best case, 5 marks. 4 to 5 marks. And weightage for ESE examination is 5 questions, 2017. 5 questions means each question 2 marks. 10 marks here. And 8 questions, 18 into 2, 16 marks. 5 questions, 5 into 2, 10 marks. And 4 questions. Roughly in ESE examinations, right, minimum of 5 questions. 5 questions, 10 marks you can expect from synchronous machines. Okay. Lastly, what to practice to gain maximum? Definitely, you need to prepare previous GATE examination paper. Anyhow, we are going to do the problems. We are going to see some questions. I am not going to discuss each and every GATE question because material is being given for you. Some typical questions, some means most of the questions, not only GATE, other examination questions also we are going to see. But you need to practice each and every GATE examination question. Previous ESC papers also, previous GATE and previous ESC. And by seeing all 10 years examination questions, you can analyze. So you can get the 100% idea how the GATE examination, how ESC examination is going to be, right? And previous PSUs and ISRO papers, previous civil services papers. Okay. Anyhow, I'm having the content of all these question papers, and during topic wise, I am going to give for each model one question. I am sure that we are going to discuss because time is limitation, and that will be sufficient. You can able to do any examination question, no doubt. Okay. So this is about the introduction. So what we have seen. So what are the textbooks and what type of what are the syllabus of our synchronous machines, right? And how many, what is the weightage in the GATE and ESC examination. So now let us start with our synchronous machines. Sorry. Just a minute, I am sharing. Okay. Yeah. Are you ready? Fine. Let us start our synchronous machines. Just a minute. Yeah. Okay. Fine. Let us start our synchronous machines. Synchronous generator. Synchronous machines, it includes synchronous machines, the synchronous machines, it includes synchronous generators and synchronous motors. Synchronous generators and synchronous motors. Synchronous generators and synchronous motors. First, I will discuss with the synchronous generators, that is alternators. After that, I will come to the synchronous motors. Of course, the most of the topics are same for both synchronous generators and synchronous motors. Thus, construction and armature reactions is a bit difference because same machine can be used as a generator and as a motor. So many topics that will be of synchronous motor also will be covered during this synchronous generator. So first let me start with synchronous generator. Synchronous generators. They are also called alternators. Synchronous generators are also alternators. Synchronous generators can be referred as alternators. So first of all, what is a generator? See, generator. There are many types of generators are there, na? There are many types of synchronous generator, asynchronous generator, that is induction generator, DC generators, reluctance generator. But any generator, we need to have so many types of generators, of course. But any generator is a machine which converts from mechanical energy to electrical energy. So generator is a machine. Generator is a machine which converts from mechanical energy to electrical energy. Okay, so you are raising doubts. I think first, before starting, let me. Can you able to see this board? Hello, so one of you, sir. Black background is best, no? Yes. Can you able to see now? Visible, na? Yes, yes. Yeah, I think background may not be possible here. You'll see. You can understand. I will write a big little whiteboard with the black color is also fine. Mostly I will use, and only sometimes I will use red color. So no problem. You can able to see. I will find out also if it is blackboard is possible. I think I never seen in this blackboard. So yeah, fine. Now let us continue, dear students. Concentrate. Your concentration is very, very important. Your focus. Okay. See, generator. Any generator is a machine which converts from mechanical energy to electrical energy. Generator is a machine. Generator is a machine, rotating machine, converting from mechanical to electrical energy. But basically, we need electrical energy in two forms. Electrical energy in two forms. What is that? We need electrical energy in the form of AC and also DC. AC and DC. Of course, most of the applications required our electrical energy in the form of AC. And few applications required electrical energy in the form of DC. Therefore, definitely we should have two types of alternators, two types of generators, DC generator and also AC generators. Yeah. So generators, two types of generators. Generators can be divided. See, generators, they can be mainly divided into two types. DC generators and AC generators. AC generators. Based on our requirement, we need electrical energy two forms, na? Yes, DC and AC. But again, in AC generators, it can be divided into two types. That is synchronous generator. Synchronous generator. They can also be called as alternator. Synchronous generator and asynchronous generator. Asynchronous generator. Asynchronous generator can also be called as induction generator. Na? Yes, can also be called as induction generator. Synchronous generator and asynchronous generator. AC generators. Of course, DC generator and AC generator, even it is a DC generator, generated EMF is AC only, correct? I think some of you might be completed DC generator. Okay. Yeah. So as I got information, almost all these machine parts are over. Transformers and induction motors are completed. Fine. And DC generators may be completed, some batches are not necessary. At least you are completed in your BTech, no? Yes, DC machines, it is the first part of that. So you may be knowing DC generator also, the induced EMF in the DC generator, in the armature winding is also AC. AC. But it is converted to AC into DC by using the commutator. Commutator converts AC to DC. Even it is DC generator, AC generated in the armature winding. You cannot generate a DC directly. Only in batteries you can get it. Any generator, it may be induced EMF or statically induced. The induced EMF may be statically or dynamically induced EMF. Induced EMFs are always AC only. Yes. If you take dynamically induced EMF, rotating machine or rotating generator, there will be poles, north pole, south pole, north pole, south pole. Poles are fixed. Na? But when conductor is passing under north pole, it can generate positive half cycle, say, as and when it is going under the south pole, it will be negative half cycle. If two pole machine within one rotation, under north pole positive half cycle, south pole negative half cycle. It is a four pole machine, north pole crosses a positive half cycle, south pole dot negative half cycle, again north pole cross, south pole dot, like that. So when conductor is rotating, it will go alternative poles, induced EMF is alternating. Even DC also induced EMF is AC. It is converted to DC by using the commutator. And we are differentiating with respect to output voltage. Across the terminal, what is voltage? Across the terminals, so across the brushes, you will get a DC. Internally, leaving. So therefore, the induced EMF will be output voltage. For DC generator, it will be DC voltage and also DC current. But when it is DC, it is only matter of voltage. What is the frequency of DC? Frequency is 0. No question of frequency for DC. Of course, inside of the armature, frequency is F is equal to Pn by 120. The armature winding of DC generator, it is AC. Its frequency also same as AC generator. Frequency expression Pn by 120 inside of the armature. But across the brushes, it is a DC, frequency 0. And AC generator means the output voltage is alternating. The voltage, output voltage with respect to time is alternating. This is AC, no? Yes. This is AC. Alternating means its magnitude is altering with respect to time. Direction also altering, alternating, changing, instant to instant. Its magnitude of voltage is changing and also direction is also changing, alternating. And where alternating voltage is there, it's a matter of voltage as well as frequency is also one of the important property. Frequency is also one of the important property of AC electrical energy. But for DC frequencies, there is no question of frequency. Frequency will be 0. AC frequency is also important. And you may be knowing, the AC generator, we will generate all AC machines. AC generators are designed to generate sinusoidal EMF. We will design our alternators or any generator, AC generator, to generate sinusoidal EMF, sinusoidal voltage. Why only sinusoidal voltage? You can generate any type of waveform. It all depends on the flux density waveform. Pole shape of the pole. If you change the shape of the pole in your machine, your waveform is going to be changed. Shape of your waveform will be changes. And you can design your machine to generate sinusoidal EMF, and also you can design your machine, your poles, to generate a sawtooth wave, rectangular waveform, right? Any type of waveform you want, you can able to generate. But we will prefer or we will generate all AC machines to generate the sinusoidal EMF, sinusoidal voltage. Why? What is the importance of the sinusoidal voltage? Because if sinusoidal voltage is there, easy mathematical analysis purpose. Because sine wave is there, integration and differentiation of sine wave is again sine or cos wave. Easy mathematical analysis purpose. Otherwise, if waveform is some type of waveform, this type of waveform, what is the equation for this? Highly difficult. If this type of waveform is given to your induction motor, three-phase waveform, say, you can't understand, first of all, what is the analysis of this performance, you cannot analyze. Right? It is said to be consisting of harmonics. We don't like it. We will generate sinusoidal EMF. If sine wave is there, easy mathematical analysis purpose, because integration differentiation relations are quite easy. Now, then coming to synchronous generator and asynchronous generator. Synchronous generator will always rotate only at synchronous speed. Synchronous generator always rotate at synchronous speed. That's the reason called it is synchronous generator. Means rotor speed. Its rotor speed NR is equal to NS. Rotor speed NR is equal to NS. But asynchronous generator, this asynchronous generator will always rotate more than synchronous speed, other than synchronous speed. Other than means generator operation more than synchronous speed. Motor will be less than synchronous speed. So asynchronous generator always rotate at more than synchronous speed. More than synchronous speed. More than ns. First of all, what is ns? That is here, it will rotate speed is equal to more than synchronous speed. What is ns first of all? Synchronous speed. ns is nothing but ns is valid only when the machine is connected to the bus bar grid. Synchronous speed is nothing but, see dear students, if this is the synchronous machine is connected on the bus bar, see it is connected on the bus bar. It may be synchronous machine or induction machine, whatever it may be. The stator, like I am taking a salient pole synchronous machine, say it is excited with DC. Synchronous machine is excited with DC. When the machine is connected on the bus bar frequency is constant, na? Voltage, and also its frequency is constant. Say for example, it is 50 Hz frequency, say 50 Hz frequency, supply frequency or bus bar voltage. This may be acting as a generator or motor. But our machine stator is three-phase winding. Stator is like this is a R phase, R dash, Y phase, Y dash, B phase, B dash. Already you might have completed induction motors. You may be knowing very well. Stator of induction motor, stator of synchronous motor, there is no difference. Absolutely same. Absolutely same. There is no difference at all. Three-phase stators are same. Induction motor, stator, induction generator, synchronous motor, their stators are same. So three-phase winding is displaced with 120 degrees spatially. R to Y, Y to B 120 degrees means on the stator, poles will form, yes, rotating magnetic field will produce. On the stator, rotating magnetic poles. See, this is north pole and this is south pole. Stator poles. But they will rotate at synchronous speed, na? Yes, they will rotate at synchronous speed. ns. They will rotate at ns. Say for example, it is some 3000 RPM. This is speed of the stator field is called synchronous speed. My dear student, speed of the stator field is said to be synchronous speed. It will rotate at synchronous speed always. Synchronous speed. It means synchronous speed is nothing but ns is equal to what? 120 into f by p. 120 into f by p. This is a relation we are also going to derive. Synchronous speed is equal to 120 into f by p means it is depends upon what? Frequency and poles. It is depends on the frequency and poles. But once the frequency is constant, say, anyhow poles are fixed. As long as frequency constant, then speed is also constant. When frequency constant, when the machine is connected on the bus bar, its frequency constant. So therefore, a machine, whenever it is connected on the grid or bus bar, so its rotating magnetic field will always rotate at synchronous speed, fixed speed. Like for example, this ns is some 3000 RPM, say, for two-pole machine. And when excitation is given, DC excitation for our synchronous machine, and here also poles will form, say for example, this is north pole and south pole. If you want to take, this is south pole, say, this is south pole and this is north pole. They are rotating at synchronous speed. Based on the given excitation, see, this is acting as a north pole, this is acting as a south pole, rotor poles. Due to excitation, DC excitation, due to magnetic locking, our rotor also will rotate at synchronous speed. Rotor also rotate at synchronous speed. That will happen only due to DC excitation. That again we are going to see. Because induction motor never rotated synchronous speed, you know, because induction motor, it is not a doubly excited motor. Induction motor rotor has to always rotate at less than synchronous speed. Generator more than synchronous speed. Then only poles will be induced. Rotor poles will be induced in induction motor. But in synchronous motor, separately exciting. We are exciting. Okay. And when stator poles rotate at synchronous speed, rotor has to rotate at synchronous speed. Then only unidirectional torque is developed. And you may be knowing, two fields are stationary. Na? Two fields must be stationary. In synchronous machine, when rotor rotates at synchronous speed, then only two fields will be stationary with respect to each other. So our synchronous motor will always rotate only at synchronous speed. If you take it as a generator, for example, if whenever I am giving the prime mover input, mechanical power input, it becomes generator. And the generator always rotating at constant speed, synchronous speed only it will rotate. If rotor rotates same as the stator field speed, that is nothing but synchronous speed. Stator field always rotated synchronous speed, rotor also rotating at synchronous speed, that machine is said to be synchronous machine. When it is acting as generator, its rotor will rotate synchronous speed. When speed is constant, then what is the frequency? Frequency will be constant. F is equal to Pn by 120. This relation also we are going to see. F is equal to Pn by 120. For a given machine, number of poles are fixed. Then frequency depends upon what? Speed. Frequency depends on the speed. If speed is constant, then frequency also constant. Speed is constant, frequency also constant. A synchronous generator will generate constant frequency. Because its speed is constant. And slip of synchronous machine. Slip is equal to ns minus nr by ns. Then what is the slip of synchronous machine? Nr is equal to ns. In synchronous machine, rotor will rotate at synchronous speed. Rotor will rotate with the same speed as that of the stator field. Then what is the slip of synchronous machine? 0. Slip is 0. Right? Yeah. So therefore, with this, now I hope you got idea. Synchronous speed is nothing but if rotor rotate with the same speed as that of the stator field speed, then the machine is synchronous machine. Rotor rotate same speed as that of the stator field. Slip is 0. Rotor never slip the stator field speed. Therefore, coming to here, nr is equal to ns. Nr is equal to ns. Then what is the slip? Slip is 0. In synchronous machine, slip is 0 and frequency is constant. It will generate constant frequency. Because speed is constant. Whereas in induction generator, nr is more than ns. When nr is more than ns means what is the slip? Slip is negative. What about frequency? Frequency is not constant. Asynchronous generator, it will rotate more than synchronous speed. More than means, for example, synchronous speed is 1500 RPM, say, 4-pole machine, 1500 RPM synchronous speed. It need to rotate more than synchronous speed. More than means it may be 1550 RPM, 1600 RPM, 1700 RPM. Variable speeds can be accepted. In synchronous machine, variable speeds can be accepted. Only condition is more than. And when speed is varying, frequency also may vary. Synchronous machine, F may vary, not necessary same. F may vary. It's not compulsory same. It may generate different frequency also. Okay. I am coming to, first of all, a question for you. why to have two types of generators? Why synchronous generator and why asynchronous generators are required? One generator is not sufficient. If only one generator is there, syllabus is going to be reduced. Correct? Yes, we will feel more comfortable. But why to have two types of generators? Suitability. Why? Because suitability. Some generators, synchronous generators are suitable for some power stations. Asynchronous generators are suitable for some other power stations. Synchronous generators are suitable for conventional power stations. Conventional means what? Conventional, thermal, nuclear, gas, hydro, and diesel. These 5 power stations are said to be conventional power stations. In that, synchronous generators are suitable. But asynchronous generators are suitable for non-conventional energy power stations. Non-conventional means like windmills, tidal power stations, etc. For non-conventional energy power stations. Okay? Some students will say non-conventional solar. Solar is different. Solar is photovoltaic system. There you are not going to use any generator. But non-conventional generators are using, they will be induction generators. So therefore, the synchronous generators are suitable. These are suitable for conventional power stations. Conventional power stations. Conventional means thermal, nuclear, gas, hydro, and diesel. Diesel power stations. These are suitable for conventional power stations. Thermal, nuclear, gas, hydro, and diesel. But these are suitable for non-conventional power stations. Non-conventional power stations. That is windmills, tidal power stations, etc. Windmills and tidal power stations. Right? They are suitable for non-conventional energy power stations. Synchronous generators are suitable for conventional power stations. Why? Can you tell me why synchronous generators are suitable for conventional and why induction generators are suitable for non-conventional energy power stations? Like wherever if you go, for example, you are in interview, you will say, first of all, why to have two types of generators? You are saying these are suitable for this, these are suitable for this. Why reason? Reason is synchronous generators are suitable for conventional because in conventional power stations, speed can be controlled. Speed can be maintained constant in conventional power stations. So for example, hydroelectric power stations, concentrate. Listen to me. Hydroelectric power stations, dam is constructed. Dam is constructed, water is stored in the reservoir consisting of potential energy. And we will brought that water through the penstock. Before impinges of the blades of the turbine, the water with high pressure, it will brought through the penstock pipes, big pipes, it will hit the turbine. Then turbine will rotate. That means the fuel is water, not fuel is water. It is coming through a proper channel. Before impinges of the blades of the turbine, I will control the water inlet by governor system, by using governor. If you open the valve of governor valve, more water and more heating takes place. If you close the valve, water is less. Okay, you can control the water inlet. You can control water pressure can be controlled. Therefore, speed can be controlled. So fuel control is possible means speed can be controlled. Speed is controlled means speed can be maintained constant. Speed can be maintained constant. Synchronous speed I can maintain. Similarly, if you take thermal power station, steam power station, we are preparing the steam in the boiler. Steam in the boiler with a very high temperature, and steam can be brought through the pipes before impinges of the blades of the turbine. So the steam pressure can be controlled, steam inlet can be controlled, so that speed can be controlled, speed can be maintained. I can rotate my machine at synchronous speed only. Whatever may be the load. If load is increases, say, I will increase my input because fuel is coming through a proper channel, I can maintain the speed constant. Load increases, I will also increase my prime mover input, mechanical power input. So that speed can be maintained constant. That is only possible in synchronous machine. But whereas if you take induction generator, in induction generator, what will happen? Windmills, say for example, windmills. In windmills, a tower is located on that wind turbine. A big tower on that wind turbine is fixed. To that generator is mechanically coupled by gearbox, through gearbox. Correct? Wind turbine speed is very less. Wind turbine speed is order of hundreds of amperes, 100 ampere, sorry, hundreds of RPM, 100 RPM, 200 RPM. But that speed is not sufficient on generator side. Wind speed is less. But generator speed must be more, means gearbox will be there. Turbine, wind turbine and generator, induction generator, gearbox will be there. 1:10 gearbox if you use, if wind turbine rotate some 100 RPM, this will rotate 1000 RPM, 1:10, 1000 RPM. That, like that, you can increase the speed. Okay, due to wind, what will happen? Wind pressure, wind turbine rotate. When wind turbine rotate, generator rotate, generator generating. But is the wind turbine speed is constant? Is the wind speed is constant? No, wind speed may changes. Seasonally, wind speed changes. Seasonally means summer wind speed is different, winter wind speed is different. Not only seasonally, day to day also wind speed changes. Morning wind speed is different, night time wind speed is different. Can you control the wind speed? Can you store the wind first of all? You cannot store. How it is coming? We need to use, that's all. We need to accept. You cannot store the wind, you cannot control the wind speed. No? Yes, that is not in our hand. How it is coming, we have to take. Therefore, speed can vary. That is nothing in our hand. Speed cannot be controlled. As the wind is coming, we need to use. Fine. But whereas hydropower station, the fuel is coming through a proper channel, so the penstock it is coming, then I can control the water inlet. That's the reason speed control possible. Here, not possible. So, these are suitable for conventional power stations. Induction generators are suitable for non-conventional power stations. Fine. And coming to among these two generators, most of the power generation is by synchronous generator. Nearly 80% of the total power generation is by synchronous generator. Most of the power generation, nearly 80%. Nearly 80% is by synchronous generators. Nearly 80% of total power generation is by synchronous generators. And that to be 2/3 of total power generation. But among this 80%, okay. But most of the power generation is by steam power stations, steam plants, thermal and nuclear. Yeah, I will go to the next page. Next page, I will continue this synchronous generator. I am comparing. In this discussion, what I want to do, two types of generator. I just want to compare what is the advantages of synchronous generator that we are discussing. So let me compare again. In the next page also, I will compare with this. Synchronous generator and asynchronous generator. Asynchronous generator means induction generator. No? Induction generator. Yeah, as I told, 80% of the total power generation is by synchronous generators. But among them, nearly 2/3 of total power generation. 2/3 means nearly 66%. 2/3 of total power generation. Total power generation is by steam plants. Steam plants means thermal and nuclear. 66% of total power generation by steam plants. Steam plants and synchronous generators we are using. And hydro, how much? hydro, by using hydro, nearly it is 13%. Hydro power generation, nearly 13%. Whereas by using asynchronous induction generator, altogether means non-conventional. What is there? Induction generator, okay, windmills, along with the solar, total, including with solar, total 21%. 21% of total power generation. So that it is 66 plus 30, 79, 69, okay, 79 percentage. This will be 79 and this is 21. Okay. Yeah. Now question for you is, most of the power generation is by synchronous generators. Most of the power generation is by synchronous generator. Okay. Why? Why? My question is, why can't you use induction generator in the conventional power stations? We do not prefer. We will prefer synchronous generators only preferred. Most of the power generation is by synchronous generator. I mean to say, what are the advantages of synchronous generator? Okay. And you may getting a doubt, sir, why you are saying induction generator means competitor for synchronous generator is induction generator. And you should know what are the differences. My topic is synchronous machine. I am coming to what is importance of synchronous machines, so that I am comparing with induction generators. Okay. Question for you is, why is most of the power generation is by synchronous generator? And what are the advantages of synchronous generator? The main advantage of synchronous generator, it deliver both active power and also reactive power. Synchronous generator, it deliver both, or generate, it deliver both P and Q, active power and also reactive power. Whereas induction generator deliver P and absorb the Q. It absorbs the reactive power. Induction generator absorbs the reactive power. Why? Because to produce the magnetic field. Magnetic field. Who is creating rotating magnetic field? Q. But for our synchronous generator, we are giving DC excitation. It can able to deliver both active power and also reactive power, generate both power. Complex power it will generate. But both powers are equally important. Na? The active power and reactive power generation is important. Being the generator, AC generator, it has to generate both power. It will generate both P and Q. Because most of the loads are inductive nature. Correct? Most of the loads are inductive nature. Inductive nature means there are different types of loads are there. Na? Industrial loads, domestic loads, commercial loads. But most of the loads are inductive nature. If you take industry, in industry, steel plants, textile mills, cement mills, there will be most of the loads being driven by the induction motor. Most of the loads are induction. Even if you take our household purpose, domestic applications, we are having fans, refrigerators, right? Fans is being driven by the motor, induction motor. Most of the loads are induction motors, inductive loads like transformers. All they absorb the reactive power. No? All they will be absorb the reactive power. Who is to supply? Generator has to supply. So synchronous generator, it generate both active power and reactive power. The power will be both powers will be transmitted through the transmission line, and load side receiving end induction motors, they will absorb both active power and reactive power. Reactive power is to produce the magnetic field, and active power is converted to mechanical power. Mechanical power for different works. So therefore, most of the loads are inductive nature means, and the generator has to deliver both active power and reactive power. Right? Yes. When active power generation must be equal to active power demand, then only frequency stability takes place. Active power generation must be equal to active power demand plus losses, of course, losses. Then only frequency stability takes place. Reactive power generation must be equal to reactive power demand. Then only voltage stability takes place. Correct? Yes. In a power system, a stable power system exists only with active power, and reactive power generation must be sufficient. Sufficient should be. You just assume like this. If all the generating stations are with induction generator, listen, instead of synchronous generator, if all the generators are induction generators and all motors definitely induction motors, then what will happen? All induction generators also absorbing the reactive power, induction motors also absorbing the reactive power. So both generators are absorbing and motors are absorbing. Who will supply the reactive power? Where is the source of reactive power? No system exists. Voltage collapse. First of all, system cannot exist. So demand must be. Inductive loads, they will absorb the reactive power, means being the generator, it has to deliver. That is the importance of the synchronous generator. It will deliver both active power and also reactive power. Right? Yes. And similarly, the another advantage of the synchronous machine, its power factor can be controlled, and both P and Q can be controlled. P and Q can be controlled. We can control the active power, reactive power. Here we cannot control. P and Q cannot be controlled. Reactive powers cannot be controlled. Active power cannot be controlled. And power factor can be controlled. In this, power factor can be controlled. Power factor can be controlled. Power factor cannot be controlled. Power factor cannot be controlled. You cannot control power factor. And it can be operated, all range of power factor can be operated at all power factors. That is, lagging, it can be operated lagging power factor, leading power factor, and UPF. Lagging, leading, and unity power factors we can operate. Lagging power factor, leading, UPF. But induction generator, it will operate only at leading power factor. Leading power factor. Correct? I think already you might have completed induction generators, induction motors. Induction motor will always operate only at lagging power factor, induction motor. And induction generator operate only at leading power factor. Opposite, motor only lagging. This we are going to see at the end of topic. In 6th chapter, I am going to explain. I will compare induction generator, synchronous generator. But you need to wait up to 6th chapter. Here just I am comparing. Don't worry, dear students. You may be saying, sir is saying active power, reactive power factor control. Just it is only for comparison purpose. Okay. But all these things we are going to see each and every point in the coming next topic. Each topic requires a lot of discussion. Right? So this is only just for introduction. How these are controlled, that we are going to see. Right? So it can be operated all power factor, but this is only leading. And it can be operated good power factor. Can be operated at good power factor. Good power factor. 0.8 to 0.9 lagging. The power factor will be 0.8 to 0.9 lagging. Synchronous generators are most of the generating station, they will be operated 0.8 to 0.9 lagging. Good power factor. But it is operated poor power factor. Comparatively, synchronous generator this will operate at poor power factor. Leading, of course, it may be some 0.5 leading, 0.6 leading, But whereas synchronous generator operate all range of power factor, lagging, leading, UPF also. If you want a unity power factor also, you can operate synchronous generator. Okay. But we do not prefer synchronous generator operating only at unity power factor. We are operating a synchronous generator operating only at 0.8 to 0.9 lagging. If you want, you can operate at unity power factor also, but we do not prefer. Why? Why? Because if you operate at unity power factor, reactive power is going to be 0. Reactive power is 0. But we want reactive power also, na? Yes. That's the reason it is 0.8 to 0.9 lagging. Power factor is good. It can generate even reactive power also. But 0.8, 0.9 power factor is good power factor. Therefore, efficiency also good. Good efficiency. Synchronous generator will have good efficiency, but this is poor efficiency. Induction generator efficiency is poor. Poor. So that's the reason. That's the reason most of the power, due to all these advantages, my dear students, due to all these advantages, synchronous generators are very popular. Total power generation, 80% I told na, maximum percentage of the power generation is by the synchronous generators, because due to all these advantages, active power, reactive power, power factor can be controlled, can be operated best power factor, efficiency is better. Correct? Yes. Okay. Now, with all these discussions, we are in a position. We are in a position to define our alternator. Therefore, I can say alternator is a machine which converts from synchronous generator, or alternator is a machine which converts from mechanical energy to electrical energy at a particular voltage but at constant frequency. It is rotating at constant speed, na? Therefore frequency also constant. So synchronous generator is a machine. Synchronous generator is a machine synchronous generator or alternator is a machine which converts from mechanical energy to electrical energy, mechanical energy to electrical energy at a particular voltage but at constant frequency. Frequency should be constant. Why? Speed is constant. At a particular voltage but at frequency constant. Frequency is the important property. Frequency is the important property of AC electrical energy. Therefore, we need to generate constant frequency at a particular voltage. The voltage level may be different, but frequency must be constant. I think you may be knowing what is the voltage generation voltage levels. Generation voltage levels, it may be 6.6 kV. It is generation voltage 6.6 kV, 11 kV, 13.2 kV, 22 kV, maximum voltage, India generation voltage 33 kV. All these are the generated voltages at different power stations, but all their frequency is how much? 50 Hz frequency. The frequency is 50 Hz. Frequency is 50 Hz frequency. All they will be. Voltage levels are different, but frequency is same. I will come to the reason why. Reasons for constant frequency. Here, frequency is the important property. Right? So we need to generate constant frequency. What is the importance of constant frequency? I will come back. So if you want to generate constant frequency means, you know, frequency depends upon what? Frequency depends on the frequency F is equal to. Frequency F is equal to Pn by 120. Na? Yes. Frequency is F is equal to Pn by 120. I want to generate constant frequency. This I need a frequency should be constant. Okay. I need constant frequency. What about number of poles? Poles are fixed. Correct. For a given machine, once a machine is designed and constructed, number of poles are fixed. you cannot change the poles. Once 4-pole machine means once designed and constructed, poles cannot be changed. Then frequency depends upon what? Speed. So if you want to generate constant frequency, the machine must be always driven only at one speed. That speed is called synchronous speed. And to generate constant frequency, poles are fixed, poles are constant, no? Yes. Then frequency depends on the speed. If you want constant frequency generation, to generate constant frequency, the rotor must be always driven only at one speed. That speed is called synchronous speed. You're getting? Yes. To generate constant frequency, the machine has to be driven always only at one speed, called synchronous speed. That's the reason these machines are called synchronous machines. Synchronous machines. And I will come back to that. What is importance of constant frequency? So now I can define our alternator. So alternator is a machine. Alternator is a machine which converts from mechanical energy to electrical energy at a particular voltage, but at constant frequency. Constant frequency. Frequency is the important property. Frequency is the important property of AC electrical energy. Frequency is the important property of AC electrical energy. So to achieve constant frequency, to generate constant frequency, the machine must be always driven. Only at synchronous speed. That's the reason these machines are called synchronous machines. That's the reason these are called synchronous machines. That's the reason these machines are called synchronous machines. Right? Yeah. Now, okay. So some of you are and keep on raising your doubts. So some hundreds of students are there. I cannot answer all the doubts now. But after the class, I will spend whatever the time you want. 2 hours you want, I will spend even up to 12 o'clock also, no problem. In between, I can't explain the doubts because if I attend your doubts, discontinuity will come. Correct? After completion of that, I will spend the time. I am going to clear all your doubts. Don't worry. Okay, first focus whatever I am saying. Listen carefully. Note down the points. Okay, so alternator is a machine which converts from mechanical to electrical at a particular frequency. Frequency is the important property. Okay, so generating station voltage levels may be different. Frequency must be same. Why? What is importance of constant frequency? Let us see. Importance of, from the beginning onwards, I am saying constant frequency. Why to generate constant frequency? If you generate different frequency, what will happen? Importance of constant frequency. importance of constant frequency generation. Why to generate constant frequency? Importance of constant frequency generation. There are two things mainly. Reasons for that two. Number one is to have the understanding between generators and consumers. Consumers means load. To have the understanding between generators and consumers, standardization of frequency is essential. First, let me write. Number one, to have the understanding between. To have the understanding. To have the understanding between generators and consumers. Generators and consumers. Consumers means that is loads, na? Yes. Generators and consumers. The standardization of frequency is essential. Standardization of frequency is essential. Standardization of frequency is essential. Yeah. To have the understanding between generators and consumers, standardization of frequency is essential. Clear? Yeah. Just let me explain this point, elaborate this point. Generators and consumers. There are generators are there and consumers. Who is the consumers? We are the consumers. Loads are the consumers. Or else we are the consumers. How we are consuming our electrical energy? Through our loads. I am not consuming electrical energy. I am not taking 10 amperes every day. Right? I am taking electrical energy through my loads. Like a fan is there, light is there, refrigerator is there. Right? So to have the understanding between generators and consumers, standardization of frequency is essential. For example, say there are 4 generators are there and 4 loads are there. Loads means induction motors you take, mostly induction motors loads. 4 generators, 4 induction motors. And 4 generators are designed at different frequencies. Say, for example, one generator is designed at 50 Hz frequency, one is at 30 Hz frequency. One generator, 30 Hz frequency, one is at 25 Hz frequency, one is at 40 Hz frequency, one is at 50 Hz frequency. And all 4 generators are designed at different frequency. And similarly, 4 loads also, 4 induction motors also designed at a different frequency. The one induction motor designed at 25 Hz frequency, one is designed for 30 Hz frequency, one is 40, one is 50 Hz frequency induction motors. Like, so an induction motor which is required, it's a supply. A 40 Hz induction motor has to be supplied where 40 Hz generation is available. From 40 Hz generator only you have to take your 40 Hz induction motor. Like an induction motor designed for 25 Hz frequency, it has to be searched where 25 Hz generation is available. Like 40 Hz generator, you have to see where 40 Hz generation is available. Some limitations are coming into picture. Some limitations are coming into picture. To avoid all these things, standardization. Yes, standardization means, yes, you people generate all your generator 50 Hz frequency. And when all generating station 50 Hz frequency means, then automatically all loads will be designed. All loads will be designed, right, for available frequency only. 50 only available. Therefore, all motors they will manufacture and will design only at 50 Hz frequency. Correct? Yes. Therefore, wherever supply is available, it is understand that it will be 50 Hz frequency so that everybody can use. So standardization. The supply is there means I don't want to measure all that. It should be confirmed that a particular frequency standard. India frequency 50 Hz, wherever you go, so that directly you can utilize. It is universal utilization. Some standardization is required. Number one. Okay, yes. Next, second one is, okay. Second one, all generating stations are interconnected through grid. All generating stations are connected in parallel. One generating station do not have its own load. All generating stations are connected in parallel. All they will be transmitted power through the transmission line, and loads are connected at the receiving end, and all they will be distributed. So all generating stations are connected in parallel means condition for parallel operation, frequency must be same. Frequency must be same. Okay, it is standardized and all they will be connected. All generating stations are connected. All generators are interconnected through grid. Interconnected through grid. Nothing but parallel operation of alternator. Nothing but parallel operation of alternator. Parallel operation of alternator. The condition for parallel operation. The condition for parallel operation. The condition for parallel operation. Frequency must be same. Frequency must be same. All generating stations should have same frequency. Okay. Frequency must be same. Voltages may be different. Yeah? Voltages may be different, but frequency must be same. And I may ask a question. For parallel operation, voltage also must be same, na? Voltage also must be same. But you are generating at different voltages. How can you connect it in parallel? Before connecting in parallel, I can step up the voltage or step down the voltage. At every generating station, transformer will be there, na? Transformer. By using transformer, I can step up or step down my voltage levels for common point of coupling. When connected to the commonly, so I can increase the voltage levels if you want to increase, or you can decrease, such that required voltage levels can be obtained by using the transformer. But by using transformer, can you change the frequency? Can you step up or step down the frequency? No. Voltages can be changed, but frequency you cannot change. That's the reason frequency is decided to generate constant frequency at generation itself. At generator itself, I can generate the constant frequency. Voltages can be changes. Okay. That's the reason, as I told, induction generator. Induction generator, speed is different. Speed is not constant. Wind speed may changes. Frequency may changes. That induction generator, you cannot connect directly to the grid. No, you cannot connect directly to the grid. What we will do? So induction generator AC, it is converted to DC by using rectifier, and again it is inverted. Wherever induction generator is there, there must be inverter and converter station must be there. So the AC at induction generator, when frequency changes, but entirely it is converted to DC, and again it is inverted to AC. But at inverter, frequency can be controlled. So at inverter, I can maintain the frequency required level. 50 Hz frequency at inverter I can maintain. Then only it can be connected to the grid. Then only connected to the grid. There onwards. But at generator, you cannot generate the constant frequency. Later, converter, inverter, at inverter, we can maintain the frequency. Then only it can be connected to the grid. Right? But a generating station, synchronous generator, at generator itself, we can maintain the speed constant, frequency constant. That is possible. Right? Yes. Okay. And as we know, the standardization, frequency standardized. What is the frequency? Our India frequency, 50 Hz. Some cases it is 60 Hz. But why the frequency generation is standardized as 50 Hz or 60 Hz? My question is, next question is, why? Constant, okay. but it is decided to generate 50, na? Yes. The question is, why the frequency of generation? Why the frequency of generation is 50 hertz or 60 hertz? 50 hertz or 60 hertz? What is the importance? Why to generate only 50, 60? Why can't you generate some kilohertz, few kilohertz? Or why can't you generate some 10 hertz? Why we are standardizing only at 50 to 60 hertz frequency? Reasons. Let us see. Reason is, I am going to explain why the frequency has 50 to 60 hertz frequency means there is a problem, lot of problems with high frequency generation. High frequency. If you generate some 1 kilohertz, say 1 kilohertz means, right, high frequency, there are the problems. What are the problems? Let us see. Or simply see here, I may raise a doubt. F is equal to Pn by 120, na? F is equal to Pn by 120. Okay. For example, if number of poles of 1000 poles I am using, say, you just imagine if I am using 1000 poles, then frequency will be order of kilohertz, na? Yes. Poles is 1000 means 1000 into n, it becomes kilohertz. But when poles are 1000 poles means what is the rotor diameter? Rotor diameter becomes very, very large. Larger rotor diameter. When diameter is larger means definitely you need to increase the speed. You need to decrease the speed. When poles are larger means definitely speed has to increase. Because poles are more means, so we need to fix to the shaft. Rotor is very larger. Large rotor cannot rotate at large speed. Definitely you need to reduce. Close speed you have to rotate. Then what is the use of? No. And at the same time you may be thinking, yes, I can rotate at some very large speed. At high speeds, say, if I rotate some 10,000, 20,000 RPM means mechanical damage takes place. Centrifugal forces. At high speeds, the machine cannot withstand. Can you rotate some 10,000, 20,000 RPM? No, large system it cannot withstand rotational forces. So let us see one by one. I will discuss first with the problems with the high frequency generation and later problems with low frequency generation. Then what is the best for 50 to 60 hertz frequency? I will come to the point 52. So let us see the reasons. The problems with high frequency generation. Problems with high frequency. Problems with the high frequency generation. The problems are, number one, with high frequency, see, with high frequency, the reactance of transmission line. The reactance of transmission line is large. Reactance of transmission line is large. Excess is proportional to frequency. Reactance of transmission line is large. Therefore, power handling capability, power transmitting capability, capability of transmission line will reduce. Power handling capability of transmission line will reduce. Correct? Because power is equal to EV by X sin delta. Power is equal to EV by X sin delta. Where E is the sending end voltage, transmission line I am talking. Sending end voltage. V is the receiving end voltage. Receiving end voltage. X is the reactance of transmission line. delta is the angle between E and V. That is, we will call load angle. Delta, power angle. But here, this is X is proportional to frequency. Na? X is proportional to frequency. X is proportional to frequency means at high frequency, what will happen? At high frequency, X is large. X is large, then power will be less. Power is less. Correct? When X is more means power handling capability. Transmission, power handling capability is going to be reduced, less. That is one problem. With high frequency, you cannot transmit high power. High frequency, power transmission is less. But that is also important thing. Na? Erection of transmission line is a big task. We need to utilize the maximum capability of the transmission line. That is not possible at high frequency. Number one. And second one is, this is taken, na? Yes. Second advantage, second limitation. Second one is more constant losses. More constant losses. Constant losses means hysteresis and eddy current losses. The hysteresis loss are proportional to frequency. Eddy current loss are proportional to frequency square. Frequency square, correct? Yes. But at high frequency, more losses. Therefore, less efficiency. Efficiency is going to be reduced. Constant loss are more. Hysteresis, eddy current losses are more. We know hysteresis loss are proportional to frequency. This is another limitation. Third one, more effect of harmonics, large effect of harmonics. Large effect of harmonics. One drawback, large effect of harmonics. And you may be knowing, nth harmonic frequency, n times of fundamentals, no? Yes, nth harmonic frequency is n times of fundamental. But when, if F is large, then Fen still large. Therefore, large effect of harmonics. Harmonics effect will be very large. When F is large means N into F still large. Large effect of harmonics. Like in induction motor, say, fifth harmonic is there. Fifth harmonic will develop the torque in opposite direction. Seventh harmonic in same direction. So rotating machines, a lot of vibrations also takes place. Correct? Large effect of harmonics. And fourth one is speed limitations. Speed limitations of turbine and generator. Because at high speeds, large centrifugal forces, rotational forces. Large centrifugal means rotational forces. Large centrifugal forces. Therefore, machine cannot withstand. Mechanical damage takes place. takes place. Okay. Yes. Mechanical limitations takes place. At high speed, it cannot be withstand. Very high speed, for example. For your information, I will give one important point here. You respond for that. For example, I want to generate F is equal to Pn by 120, na? Pn by 120, Pn by 120 say. I want frequency is equal to 1 kilohertz. 1 kilohertz say. 1 kilohertz means how much it is? 1000 hertz. 1000 hertz. If poles is equal to 2 say, for example, if P is equal to 2, when P is equal to 2 means what is N? N is equal to 60,000 RPM. 60,000 RPM you have to rotate. Correct? P2, 2 by 60, and 60,000 RPM. Will the machine withstand that 60,000 RPM, dear students? Will it withstand 60,000 RPM if you rotate? 1 kilohertz, can you generate? Impossible. Practically impossible. It cannot withstand. Not 60,000. Even 10,000, it cannot withstand. And not only that, who will rotate 10,000 RPM? Can you rotate 60,000 RPM by using any turbine? Is it practically possible? Not possible. Steam or water, whatever it may be, it's only few thousands of RPM. You cannot rotate very high speed, high frequency. Okay, these are the limitations of high frequency generation. And next one is low frequency generation. Next point is low frequency. Problems with low frequency. These are the problems with high frequency. Okay. Now let us see problems with low frequency. Problems with low frequency. With low frequency generation or low frequency. Problems with low frequency. Number one, flickering of the lamps. Flickering of the lamps. At low frequency, lamp will flicker. For example, in our frequency is 50 hertz, no? 50 hertz or 60 hertz. 50 or 60. With that, we can able to see the lights, continuous light you can find. But whereas if frequency 5 hertz say, very low frequency 5 hertz say, lamp will flicker. You cannot see the lamp continuously. It will dark bright it will take place. At very low frequency. Correct? 50, 60 hertz is best. Okay? Flickering of the lamps. And second one is, with low frequency, size of the machine is large. Low frequency machines will be their size, weight large and cost also large. With low frequency, large size of the machine. Large size of machine. Therefore, more cost, large weight, more space occupation. It will occupy more space occupation, and transportation problems also. All these are the difficulties. When frequency is less means size of the machine is more. Low frequency for a given power. With low frequency, large size of machine for given power. If you want some 500 kilowatts, say 500 megawatts, if you want to say, at low frequency, size is very, very large. Yeah, that is a problem. Problems with low frequency. And we have discussed problem with high frequency. Not only that, efficiency point of view also. We need to take care about efficiency point of view also. You may be knowing overall efficiency of our generator. Overall efficiency is equal to what? Efficiency of the turbine efficiency, boiler efficiency. First, let me take boiler efficiency and turbine efficiency into and generator efficiency, alternator efficiency. Steam power plant. If you take steam power station, the overall efficiency depends on the boiler efficiency, right? Product of turbine efficiency and generator efficiency. And boiler efficiency is nearly 90%, good efficiency boiler. But turbine will have 45% efficiency, steam turbine. Generator will have 93% efficiency, 93%. So that overall efficiency is a 37%. 37%. This is for our steam power station, steam plants, for steam power station. This is for steam power station. For steam plants. Steam plants. Order of 30, 37%, 30, 40% ante kada. Thermal power stations, thermal power station efficiency is that much only. 35, 40%. But hydro, it will have no doubt good percentage efficiency. 70% order of hydro power station. But steam power stations, poor efficiency. So here, which is having very less efficiency? Turbine is having less efficiency. Steam turbine will have 45% efficiency. But turbine efficiency depends on the speed. Turbine efficiency depends on the speed. That's the reason. And the steam turbine will have good efficiency at a speed range of 3000 RPM. Steam turbine will have good efficiency, high speed only. We'll always prefer at high possible speed. But limitations also there at high speeds. A steam turbine. Are you getting here? Main important thing is which is having poor efficiency. The turbine is very less efficiency. Turbine efficiency is very less. But we need to take care about efficiency. But turbine efficiency, that will be good efficiency. Even 45 is itself good. That efficiency will be for the speed range of 3000 to 3600 RPM. So the next point is the steam turbine with good efficiency. We need to take about mainly steam turbine. The steam turbine with good efficiency, for the speed range. For the speed range 3000 to 3600 RPM. 3000 to 3600 RPM, good efficiency, good possible efficiency for steam turbine. 3000 to 3600 at high speed only. 3000 means very large machines. In generating station, very large machine. 3000 RPM is large. We will prefer high speeds only. But very high speeds means machine cannot withstand. 3000 to 3600 RPM optimum with good efficiency. But to withstand this high speed, these high speeds, rotor diameter must be smaller. Rotor dia must be smaller. Rotor diameter must be smaller. Of course, rotor diameter is proportional to number of poles. Rotor diameter is proportional to number of poles. Because they are fixed. Poles are fixed to the rotor shaft. Poles are fixed to the rotor shaft. So it should have smaller diameter. Rotor dia is proportional to number of poles. But we want the rotor diameter must be smaller. Therefore, minimum number of poles are preferred. Therefore, minimum number of poles, because diameter must be smaller, na? Minimum number of poles are preferred. That is how many? That is 2 poles. 2 poles is preferred. 2 poles is preferred. With minimum poles, 2 poles is preferred. And we know poles are 2 poles, but this is the speed range. For this speed and this poles, then what should be the frequency possible? Frequency of generation. F is equal to Pn by 120. Pn by 120, P is equal to 2, N is 3000 RPM divided by 120. That is equal to how much? 50 Hz frequency. 50 Hz frequency. If it is 3600 RPM by 120, how much it will be? 60 Hz. 60 Hz. 60 Hz. So, the steam plants will have good efficiency at 50 to 60 Hz for power generation. Steam plants with good efficiency for power generation at 50 Hz frequency, 50 or 60 Hz frequency, 50 Hz or 60 Hz frequency, 50 Hz or 60 Hz frequency. Okay. The best possible efficiency for 50 to 60. Right? Hydro, no problem. Hydro at any frequency, it is okay. But most of the power generation is by steam plants. Most of the power generation steam plants, they should have definitely good efficiency. 50 to 60 Hz. Then all other generating stations also must be 50 to 60 Hz power station. 60 to 50 Hz frequency generation. Okay. This is the reason. The story why generation frequency is decided 50 to 60 Hz frequency. Because that is good efficiency. 50 to 60 Hz you will get. And also we have seen problems with high frequency, problems with low frequency. Okay. Yeah. So up to now, what we have discussed is, before going to the break, what we have discussed so far, we have seen what is the importance of synchronous generator compared with induction generator. Why most of the power generation is by synchronous generator. What are the advantages we have seen, right? And also we have seen why frequency of generation is constant. What is importance of constant frequency we have seen. And why frequency of generation is 50 to 60 Hz frequency, that we have seen. Okay. So now it is better to take the break. Right? What is your break time? Tell me just normally how much break time they are taking. One of you type in the chat box. What is normal your break time? How much? Because you might be habituated for that now. Yes. So therefore I need to take the same time. 20 minutes. Okay. 15 to 20 minutes. Yeah. Let's take 20 minutes. It may be better. Ideal. 15 minutes is too less. 30 minutes is little more. 20 minutes let us take. Maximum 20 minutes. Okay. Don't worry, I am going to clear all your doubts at the end. End of the class, I will stay here only. Fine? Don't worry. But in between, I cannot explain the doubts. Once I am attending the doubts, other people will just see like that. No? Okay. Take the break and then come back. Break for 20 minutes. Again, class will start. It is 7:30 na? 7:30, 7:50. Class will start at 7:50. Yeah. So you came back. Yeah, people are still joining. So I have given 20 minutes. You will be taking more than 25 minutes. Okay. Class is up to what time? What is the time that is given in your schedule? Just type that. What is the up to 9 or 9:30 they have given? What is the time? 4 hours. Okay. Yeah, 9:30. Fine. Yeah, we will take 9:15 or 9:30. You don't worry about the timings. We will take as comfortable. We believe that we are going to complete the syllabus in specified time. Okay. Yeah. Now, then let us start our topic. This continuation is principle of alternator. Next topic is principle of alternator. Okay. Principle of alternator. Sorry. Principle of alternator. Yeah. So are you ready? Yes. Principle of alternator. Alternator works on the principle of Faraday's law of electromagnetic induction. It may be DC generator or synchronous generator. There is no difference. Both works on the principle of Faraday's law of electromagnetic induction. Alternator works on the principle of Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. So what is the Faraday's law? I think already you may be knowing this. Faraday's laws, very basic things you might have seen many times, but even though, so it is our, definitely we need to discuss this principle. Without the principle, there is no meaning of it. So alternator works on the principle of Faraday's law of electromagnetic induction. So according to Faraday, whenever flux linkages changes in a coil, an EMF will be induced in that coil. So according to Faraday's law, whenever flux linkages changes in a coil or conductor, say coils may be in the form of conductor. Whenever flux linkages changes in a coil, an EMF will be induced. In that coil or conductor. Whenever flux linkages changes in a coil, an EMF will be induced in that coil. This is the Faraday's first law. Correct? This is the first law. And the magnitude of induced EMF, the magnitude of induced EMF is proportional to magnitude of induced EMF. Induced EMF is proportional to rate of change of flux linkages. Rate of change of flux linkages. Magnitude of induced EMF is proportional to rate of change of flux linkages. This is second law. Faraday's second law. Faraday's first law and Faraday's second law. According to Faraday, induced EMF is proportional to rate of change of flux linkages, d phi by dt. Is proportional to rate of change of flux linkages. That induced EMF is equal to minus n d phi by dt. D phi by dt, where n is the number of turns, d phi. D phi is the change in flux. Change in flux in time dt seconds. Dt seconds. Of course, change in flux in Webers. Change in flux in time dt, where n is the number of turns. N is the number of turns. So according to Faraday, whenever flux linkages changes in a coil, dear students, taken this. Yes, where are you? Listen, take it little faster. If those who are writing, please make it faster so that let us have continuity. Continuity. A lot of discussion will be there now in the machines. Yes. Okay, but I will write everything on the board. You don't worry. But at the same time, better if you write also, that will be synchronization. No? When you are writing also, you can think about. Okay. Yeah. Listen. According to Faraday, whenever flux linkages takes place in the coil, whenever change of flux linkages, whenever flux linkages changes in a coil, an EMF will be induced in that coil. Say for example, this is a coil, this is a coil, this is a magnet. When magnet is moving inside of the coil, flux linkages takes place. In this coil, when flux passing through the coil changes, EMF is induced. Flux passing through the coil. Flux linkages means what? Flux passing through the coil changes instant to instant. So for example, now flux linkages is 1 milliwebers. Is passing. This is a coil, say. Flux linkage 1 milliwebers. Next to 2 milliwebers, 3 milliwebers, 10 milliwebers. Like as the flux changes, EMF is induced in the coil. This is given by the Faraday. In the year of 1831, he has given that. In the 1831. And proved that results. Laws will have practical results, na? Yes. And he observed that the flux passing through the coil, flux linkages changes, and EMF will be induced in that coil. Is given in the year of 1831. Right? It's a great man, na? Faraday is a great man. Faraday is the godfather of electrical engineering. Have you seen at any time Faraday? I mean, photo of Faraday. You can search in the net. Google, you can search photo of a Faraday, because he's a godfather. We should know all of the electrical engineering must see the Faraday, photos of Faraday, biography of Faraday. Great man, no? Without Faraday, there is no generator, no? Without Faraday, there is no generator. If there is no generator, there is no electrical engineering. If there is no electrical engineering, there is no GATE examination, there is no ESC examination. Fine. So if you are here, I am here. All of are here because due to Faraday. Fine. So great man. So he has experimented that whenever flux linkages changes in a coil, flux passing through the coil, linkages means what? Flux passing through the coil changes, and EMF will be induced in that coil. Is given by the Faraday. That is the first law. And second law is how much induced EMF, magnitude of induced EMF. The magnitude of induced EMF is proportional to rate of change of flux linkages. d phi by dt, rate of change of flux linkages, and that E is equal to minus N d phi by dt, where N is the number of turns. And first of all, why this negative sign? Negative sign is according to Lenz law. Negative sign is according to Lenz law, and that induced EMF is governed by the Lenz law. The direction of induced EMF is decided by the Lenz law. And the direction of induced EMF is such that the current produced by EMF will set up a magnetic field which opposes the change of flux linkages. Change of flux linkages. Let me write that point first. Negative sign is according to Lenz law. Minus N d psi by dt, na? Negative sign is according to Lenz law. Lenz law. The direction of induced EMF. The direction of induced EMF is governed by Lenz law. Lenz law. The direction of induced EMF is such that the direction of induced EMF is such that the current produced by it, the current produced by it will set up a magnetic field, will set up a magnetic field which opposes the change of flux linkages. Change of flux linkages. Direction of induced EMF is such that the current produced by it will set up a magnetic field which opposes the change of flux linkages. It opposes the change of flux linkages. Right? Direction of induced EMF you can find by applying the Lenz law. According to Lenz law, effect and cause relations, cause and effect. What is the cause? What is the effect? Effect is induced EMF. You are getting induced EMF. Induced EMF. And by induced EMF, what happened? Magnetic flux. Induced EMF is there, magnetic flux is there. But what is the cause for that induced EMF? The cause for that is change of magnetic flux. Change of magnetic flux. Or change of flux simply. Change of flux. Change of flux linkages. Effect is induced EMF. Cause is change of flux linkages. But where induced EMF is there, it will produce the current. Induced EMF will maintain the current and that will produce the magnetic field. Magnetic field. Therefore, according to Lenz law, the effect always opposes the cause producing it. The effect always opposes the cause producing mean the magnetic field always opposes the change of flux linkages. Change of flux linkages. According to Lenz law, the effect always opposes the cause producing it. The effect always opposes the cause producing it. Cause producing it. So effect is the induced EMF. Effect and result. Induced EMF we are getting, that is producing the current, that is producing the flux. But what is the cause for induced EMF? Change of flux linkages. When flux linkages changes, EMF will take place. But that EMF will produce the current and that will produce magnetic field. That field opposes the change of flux linkages. Okay? Yes. So this magnetic field opposes the flux linkages. For this field, causes flux linkages. Okay. So for example, let me take a simple example before coming to a practical machine. Practical machine. See. See here. This is a toroid. On this, I am keeping a coil. See, I am keeping a coil. Right? This is a coil. Now, if you take a magnet, this is the permanent magnet, say, permanent magnet. This side is north pole, this is south pole, north pole, south pole. And its magnetic flux lines will be, how the magnetic flux lines? North to south. Its flux is from north to south. These are the magnetic flux lines, north to south. Yeah. Flux. If this magnet is moving in this direction, see, if the magnet is moving in this direction with a linear velocity of v meters per second, when magnet is moving, what is happening? The magnet will move inside of the coil. Instant to instant flux passing through the coil changes, na? Yes. When magnet is more inside, more flux linkages. It is moving. This is a coil, say. When magnet is moving inside, more flux linkages. But flux linkages in which direction? The flux linkages, this is D psi, say. Change of flux linkages in this direction. Change of flux linkages. When change of flux linkages in this direction means an EMF will be induced. In which direction? The induced EMF will produce the flux in opposite direction. It will produce the flux in opposite direction. It means I want to get flux will be in this direction. D phi must be in this direction. D phi induced flux must be in which direction? It should be in this direction. Must be in this direction. In this direction means now what should be the current direction? Apply your thumb rule. By applying the thumb rule, the current must be in this direction. Current must be in this direction. When current is in this direction, it is producing the flux in this direction. Na? Yes. The induced flux will be in this direction. Induced flux must be. So this is D phi, but induced flux will be in this direction. The current is in this. Means these are the EMF polarities. If you connect a load here, this is plus and this is minus. Current will passes from the positive terminal. Na? Yes, positive terminal. So therefore, in this direction is the direction. Thing is, the current direction will be in such a direction. This is the current. Induced EMF will drive the current in opposite direction, that of the magnetic field. Okay. Fine. This you may be knowing already, you might have seen in transformer. But practical machine, it is not like that. Now, practical machine, it cannot move linearly. Here, whatever the diagram I have shown, linearly it is moving. But practical machine, it is not like that. It is a rotating machine. But there are two types of induced EMF, statically and dynamically induced EMF. Important thing is here, how change of flux linkages is created. Ultimately, how to flux linkages must be changed. The change of flux linkages, rate of change of flux linkages can be created in practical machines by two ways. Either by relative space variations or by relative time variation. Yes, students, now I am coming to the important thing. These things you may be knowing. Okay, are you ready? These things, very basic things, because without this, I cannot move. That's the reason I am explaining. Okay, now I am stepping into our practical machine. So according to Faraday, whenever flux linkages changes in a coil, EMF is induced. But how we can create in practical machine flux linkages? How we can create change of flux linkages? Two ways. Number one is by relative time variation or by relative space variation. Let me write first that we are going to see with the diagram. In practical machines, change of flux linkages. In practical machines, change of flux linkages. Change of flux linkages can be created either by relative time variation, or by relative space variation, by relative time variation or by relative space variation, both. Time variation, space variation. Let us see one by one. What is the meaning of and how you can create by relative time variation? First one is the change of flux linkages. Change of flux linkages by relative time variation. Change of flux linkages by relative time variation. It requires magnetic field is magnetic field. Magnetic field must be time varying field. Time varying magnetic field. AC field. So it must be excited with AC, time varying field. And there no need of any relative motion. Both coil and stationary. No relative motion is required. Between field and coil. No relative motion is required. And how change of flux linkages? By relative space variation. Next one, change of flux linkages by relative space variation. Change of flux linkages by relative space variation. Here by relative time variation, first I am writing and we are going to see very clearly what is the meaning of relative time variation, relative space variation. Change of flux linkages by relative time variation, it requires magnetic field is time varying field, time invariant field. That is steady field. The DC field, in other words. Steady field means what? DC excitation. Steady magnetic field. And there must be relative motion between. Relative motion between magnetic field and coil. Relative motion between magnetic field and coil. Time variation, first one, no relative motion is required. No relative motion between field and coil is required. But whereas dynamically induced EMF, there must be relative motion. Whereas field is excited with DC. DC. Of course, in two cases, induced EMF will takes place now. In two cases, induced EMF. But in this case, first case, it is said to be, induced EMF is said to be statically induced EMF. Correct? This is statically induced EMF. No relative motion between both. Field is not rotating, coil is not rotating. Statically induced EMF. But in the second case, it is a dynamically induced EMF. This is dynamically induced EMF. Statically, dynamically. And can you tell me the example for statically induced EMF? Statically induced EMF. Best example is transformer. Transformer induced EMF is statically. Dynamically induced EMF in all rotating machines. The example is in all rotating machines. In all rotating machines, dynamically induced EMF takes place. If you take DC generator, induction generator, synchronous generator, dynamically induced EMF takes place. Whereas statically induced EMF in transformer. And mainly, right, mainly in both cases, the difference is, first one is statically induced EMF. It is time varying field. Time varying field means AC field. But here it is DC field, time invariant field. And another difference is relative motion. There is a relative motion. First one is no relative motion, second one is relative motion. So just I want to explain why here it is time varying, why time varying field is required, and why it is a relative motion is required. I want to clear that points mainly. Okay? Yeah. Let me take here the two diagrams. With that, we will see. Yeah. You know very well about the transformer. I will draw the similar kind of diagram for transformer for easy understanding purpose. See. Already you are completed transformer. Okay. Is a transformer core on this is the primary winding is excited with AC, no? Excited with AC. This side is secondary winding. Yeah. Right. Primary is excited with AC. V is equal to Vm sin omega t, say. When it is excited, the flux will passes through this. Correct? The flux passes through this. Flux will be passes like this. See, this is the flux. Flux passes inside of the coil. Flux passes inside of the coil. But that flux is it constant or changes with respect to time? Flux changes with respect to time. This is the flux, say, flux. But flux passing through the coil changes. That is the flux linkages. First of all, one point I would like to write. Flux linkages means this point must be clear. Flux linkages means flux passing through the coil. Flux passing through the coil. Flux passing through the coil. That is flux passing inside of the coil. Flux passing inside of the coil. Flux passing inside of the coil. If all flux lines are passing inside of the coil, then flux linkages is maximum. If all flux lines are going outside of the coil, flux linkages is minimum. Clear? Flux linkages means flux passing through the coil, flux passing inside of the coil. Okay? Yeah. And whenever if you take as a transformer core is rectangular core, no? Transformer core is rectangular core. On that you are keeping the winding. So coil also rectangular, core also rectangular. And whatever the flux the core produce, it will passes inside of the core. It will passes inside of the core means flux link, all flux lines are passing. But the flux is varying with respect to time. Flux is varying with respect to time. Since we are giving AC, then how flux will be? Time varying nature, na? Yes. Is the current is AC and flux also time varying nature. Flux is time varying nature. Flux is time varying nature. With respect to time, it is AC. AC means how flux lines are changes. Flux is changes. Here flux is 0. Here flux increases. 0 milliwebers say. Here 2 milliwebers, 3 milliwebers, 5 milliwebers, 10 milliwebers maximum. And again flux decreases. No? Flux decreases. Instant to instant, as current changes, flux also changes. Same flux passing inside of the coil changes. So flux passing inside of the coil means there will be induced EMF. EMF will be induced in the primary as well as EMF will be induced in the secondary also. But here magnet is not moving and field is not moving. They are stationary. Only thing is statically induced EMF required time varying field. The field is varying with respect to time. Now I will ask one question for you. If you give DC, what will happen? If you give DC, say for example, when DC is given, flux also constant, no? Flux is constant. For transformer, when DC is given, there will be no induced EMF. Transient condition, you leave it. Because it is inductance, it will not allow sudden changes in current, leave it. But steady state condition, current is constant, DC given. When current is constant, flux is constant. When flux is constant means flux passing through the coil, correct. But always flux is constant only, constant flux only passing. Then there will be no induced EMF. Because no change is important. So for transformer, by time varying nature, it changes, induced EMF. Same diagram I will take. Similar diagram, but I will rotate the coil, relative motion. Let us see. Here, I'm taking a coil, but I'm cutting this secondary side. Let me draw a little smaller one because I need some space. Okay. See here. Yeah. Secondary side. Yes. Here I am giving the DC excitation. Yeah. and this side a coil is being driven. The coil is rotated. See, this is a coil, but it is a multi-turn coil. A multi-turn coil is rotated. The coil is rotating. Coil is driven. Coil is not stationary. Coil is rotating. The primary is excited with DC. When primary excited with DC, current is constant, na? Yes. Current is constant. When current is constant means flux also constant for this. Flux is constant. And when based on this current direction, flux direction, this is the flux direction, no? Yes. The flux is passing like this. Flux is passing. This is a flux. Okay. Of course, this flux is constant. Flux is constant. Just a minute. Listen to me, dear students. Stop writing. Let me have continuity. Dear students, stop writing. Stop writing. Listen to me. This is a coil. Stop writing. See, this is a coil. This is one side of the coil. This other side of the coil. One side of the coil. This other side. It is having a multi-turn coil. Say, multi-turn coil. Okay. Stop writing. Listen. How transformer core? It also will have some width and some length. Na? Rectangular shape. Rectangular shape will have some width and length. Rectangular shape. See, that dimensions and these dimensions are same, but this coil I am cutting, this secondary portion I am cutting like this. I am cutting. Primary side I kept DC excitation, and this coil is being driven. Coil is rotated with some prime mover. Say, coil is rotating in clockwise or counterclockwise direction. See this diagram. So flux is coming like this. Now flux is coming. Flux will always passes through the core only. It is minimum reluctance. So whenever coil is like this, see, flux constant. Coil is like this. All flux lines are passes inside of the coil. All flux lines are passes inside of the coil. When coil is here, core is like this. All flux lines are passes inside of the coil. Inside. Flux linkage is maximum at this instant. At this instant. But when coil is rotating, say, when coil is rotating, some flux lines are passing inside, some is going outside. And if you take coil like this, what is happening? The core width is this much. All flux lines are passing outside of the coil, not inside, not inside. Because the core is here, all flux lines are passing outside of the coil, outside. But here it is maximum, like this. If you keep like this, all flux lines are passes inside, like this. Okay, core is here, na? All flux lines are passes. Flux linkage is maximum. But when rotating, you put 10 milliwebers here, 10 milliwebers. After rotating some angle, right, 5 milliwebers is passing, 5 is passing outside. And after 90 degrees, all flux lines are passing outside of the coils, outside of the coil, outside. I mean to say, I hope you can imagine. Okay, like this. All flux lines are passes. When coil is like this, all flux lines are passes maximum. Yeah. For that, if you draw the diagram, the flux linkages, I am taking flux linkages like this. At this instant, I am taking as a beginning, all flux lines are passes. Therefore, flux linkage is maximum, maximum. When it is rotating, some flux constant at 10 milliwebers, some is going inside, some is going outside, changes. After 90 degrees, when coil is rotated 90 degrees, at this position to coil rotated 90 degrees, it is rotating. Coil rotated 90 degrees means it will be 0. And again, if you take the flux linkages for 90 degrees, another 90 degrees, it is in reverse direction. Reverse direction means this is the plane of the coil. One inside, after 180 degrees, the plane will changes, na? Plane changes. This my hand is a coil, say, all flux lines passes. Okay, When rotating, some is passing inside. After 180 degrees, all flux lines are passing this side. This is negative side I will take. So therefore, so for every 90 degrees, what is the flux linkages? Flux linkages changing continuously. Though DC flux is constant, DC flux constant 10 milliwebers, but how much it is passing inside of the coil, that is the linkages. The passing inside of the coil rotating, passing inside of the coil, it changes, instant to instant it changes. Therefore, an EMF will be induced in that coil. EMF is induced in that coil. Fine? Yes. So that is the induced EMF. If you take this is induced EMF, this is the flux linkages. If indeed flux linkages is a cos wave, induced EMF will be sine wave. A main important point I would like to say here, flux is constant, but when relative motion is there, induced EMF. First one, time is time varying flux. Flux is time varying flux, no relative motion. So conclusion is, what we observed is, dynamically induced EMF required constant flux, but change of flux linkages, rate of change of flux linkages created by relative motion, rotation. If coil is not rotating, what will happen? Coil is not rotating, flux linkage is always maximum only, no change. Always maximum. Now also 10 milliwebers, after time also 10 milli, after some time also 10 milliwebers, no change, no induced EMF. No change. Linkages is maximum, but no change means no induced EMF. But who will create change of flux linkages? By relative motion. So the conclusion is, dynamically induced EMF required. Dynamically induced EMF required steady flux. Dynamically induced EMF required steady flux or time invariant flux. Let me write time invariant flux. Time invariant flux, that is steady flux. Steady flux. Therefore, field winding must be excited with DC. Therefore, field winding must be excited with DC. Excited with DC. But whereas change of flux linkages, can be created by relative motion. Can be created by relative motion. That is rotation. Relative motion or rotation. Rotation will create relative motion, flux linkages. Yeah. Relative motion will create change of flux linkages. Fine. That is the importance of the relative motion. Same, both are similar diagrams, na? But I excited DC. When I am rotating, I am getting. Okay. Now, with this discussion, I can say Faraday's law in simple form. Let me start with conductor and thereby coil, right? Thereby practical machines. We are approaching towards the practical machines means first we are going to take a single conductor. To Faraday's law in simple form. See, whenever coil is rotating, flux linkages changes. No? This coil earlier I have taken. No? When this coil is rotating, flux is passing inside of the coil, but when coil is rotating, the coil is cutting the flux. EMF is induced. Can I say, whenever a coil cut the flux, EMF is induced? Yes. When rotating, it cut the flux, are conductors. Conductors are coil. In other words, the Faraday's law in simple form, whenever a conductor cut the flux, EMF is induced. The cutting is, we can easily understand. Flux linkages, instead of saying, simplest thing, rotating machine, cutting of the flux. Whenever conductor cut the flux, EMF is induced. When rotating, it cuts. Therefore, Faraday's law in simple form, I can write like this. Simple form. Whenever a conductor cut the flux, whenever a conductor cuts the magnetic flux, an EMF will be induced in that conductor. An EMF will be induced in that conductor. An EMF will be induced in that conductor. It's a Faraday's law in simple form. Faraday's law in simple form. Some textbooks you can find this definition. Faraday's law can be defined like this. Whenever conductor cut the flux, EMF is induced in the conductor. Or coil also you can see. Conductor cut the flux, EMF is induced. Therefore, I want to generate EMF. This is my output. To generate the EMF or voltage, what is the requirement? One is the conductor. One is conductor. Another one is magnetic flux. Magnetic flux. Okay. Third one is relative motion. Cutting to takes place means what is required? Relative motion. Relative motion will create the cutting. So, requirements for dynamical induced EMF. Requirements for dynamical induced EMF is requirements for dynamical induced EMF. Number one, conductor or coils. Conductors. This later we are going to call armature conductors. Armature conductors. Armature conductors. Second one is magnetic flux. Magnetic flux, or simply we can call it as a field. Magnetic flux, that is field. Field. And third one is relative motion between conductor and magnetic field. Relative motion between magnetic field and conductor. And conductor. There must be relative motion between magnetic field and conductor. That is the these are the three requirements. First, let me call conductor. Later, I am going to call coil. Both meanings are same. Coil will have two sides of the coils. Na? Two conductors will form a turn. That is a single turn coil. First, let me take with the conductor. So, requirement for dynamical induced EMF, three things. One is the conductor, one is magnetic flux, another one is relative motion between both. So, to discuss this, let me take a single conductor. Magnetic flux will be produced, a set of magnetic poles. Okay. So, to continue this discussion, let me take a conductor. So, taken this up to here. See. Is a magnetic pole. Magnetic pole, and this is another pole. Yeah, this is North Pole. So this is South Pole. North Pole, South Pole. Magnetic flux is from north to south. This is a magnetic flux. North to south. Flux direction. This is a flux. Let me take a conductor. This is a conductor. The conductor. And the conductor is moving linearly upwards direction with a linear velocity of v meters per second, and the flux density v. This is the flux density v. It is moving upwards direction with a velocity of v meters per second. Flux density v. Angle between these two is theta. This is theta, say. Theta is the angle between this. Yes. Taken. Yeah. This is a conductor. Flux is north pole to south pole. This is north pole and this is south pole. Flux is passing from north to south. North to south. Listen. Theta is the angle between B and V. So for example, this conductor is moving parallel to the flux lines. Dear students, this pen is a conductor. When conductor is moving parallel to the flux lines, then theta 0. Theta angle between B and V, B in this direction, V also in this direction. So conductor is simply moving parallel to the flux lines. So it is not cutting any flux. Therefore, what is EMF? 0. When theta is equal to 0 means EMF also 0. It is simply moving parallel, no cutting. But for flux cutting action, conductor has to move with some angle. It has to move with some angle. But when conductor is moving exactly perpendicular to the flux lines, maximum flux cutting. Maximum flux cutting. If it is theta 90 means maximum flux cutting action, induced EMF is maximum. But when theta is 0, EMF is 0. When theta 90 degrees, EMF is maximum. Therefore, EMF is proportional to sin theta. Induced EMF is proportional to sin theta. When theta 0, sin 0, 0. Theta 90, EMF is maximum. Therefore, I can write the expression for induced EMF. E is equal to BLV sin theta. No derivation is required. I am going to derive only some important derivations now. Yes. For ESE students, after prelims, we will do the derivations, required derivation. All derivations I am going to do. For GATE peoples, it is not required. Some important derivation, conceptual oriented derivations, we will do it. But this induced EMF is equal to BLV sin theta, well-known equation, where B is the flux density. B is the flux density in Webers per meter square or Tesla. It is Webers per meter square or Tesla. L is the active length of conductor in meters. Active length of conductor in meters. Correct? Yes. V is the linear velocity. Linear velocity of conductor in meters per second. Linear velocity of conductors in meters per second. Theta is the angle between B and V. B and V in electrical degrees. In electrical degrees. Then E is the induced EMF in volts. E is the induced EMF in volts. is the induced EMF in volts. Fine. Induced EMF in volts. Of course, nobody will ask the derivation of this equation, but in the examination you may get a numericals on this. Numerical means you will be given B value, L value, V. Then you will ask what is the maximum induced EMF. The maximum induced EMF is equal to for sin 90, the BLV. Important thing, how he is giving the questions on this, he is giving B. Actually, B must be Webers per meter square, Tesla, Webers per meter square. If it is given Webers per centimeter square, say, you need to convert that into Webers per meter square. Because options, all A, B, C, D options will be given in volts. When you will get volts, B must be in Webers per meter square. If it is given Webers per centimeter square, you have to change. Webers per 10 power minus 4, you have to multiply. Similarly, length, active length of the conductor must be given in meters. In meters, then only your voltage will be V. If it is centimeters like that is given, you need to convert that into meters. And V, linear velocity, it must be meters per second. Meters per second. So all the units are important. Okay. Yeah. If it is angular velocity is given, say, you can convert that into linear velocity. You need to convert. Then only you substitute. Then only you will get induced EMF easy. Anyhow, later we are going to see some problems based on this, right? But units are important. Problems are important. Okay. So the induced EMF magnitude is depends upon what? It is depends on the flux density, active length of the conductor, and linear velocity, sine of the angle also. This the magnitude is depends upon all VLV. Then direction of induced EMF. Direction of induced EMF can be found by applying the Fleming's right hand rule, or flat form rule, or Lenz law, or cross product. Anything can be. Mainly, the induced EMF, dynamical induced EMF, you can find by applying the Fleming's right hand rule. So according to Fleming's right hand rule, what it shows? Four-finger flux direction, thumb motion of the conductor, center finger, direction of induced EMF. Four-finger flux, thumb motion of the conductor, center finger, direction of induced EMF. So let me write first. The direction of the flux can be direction of induced EMF can be found. The direction of induced EMF. The direction of induced EMF can be found by applying Fleming's right hand rule. Fleming's right hand rule. What is Fleming's right hand rule? If forefinger indicates direction of flux, forefinger indicates direction of flux, thumb indicates direction of motion of conductor, then center finger indicates direction of induced EMF. Direction of induced EMF or current. Direction of induced EMF or current. Forefinger flux direction, thumb motion of the conductor, center finger indicates direction of induced EMF. But three fingers must be mutually perpendicular. I think you may be knowing very well about the right hand rule. But even though we have to go through this, correct? You may say, sir, we know already Fleming's right hand rule, left hand rule. Even you are knowing, I need to explain. These are just like Ganapati Puja. Every day you have to do. For machines, 4 members are coming. Say 4 members will explain right hand rule, left hand rule. You have to bear. Because without this, we cannot move forward. No? Yes. So, Direction of flux, forefinger flux, thumb motion of the conductor, center finger direction of current. Okay. But even some students, they are not confident enough to apply the right hand rule. Yes, they can't apply confidently. Simple diagram is given, they can explain. But a typical diagram is given, they can't explain. They can't able to apply. Okay, let us apply for this diagram. What is the direction of induced EMF? See. Three fingers are mutually perpendicular. Three fingers mutually perpendicular. Four-finger flux direction. Four-finger flux direction. Thumb motion of the conductor. Thumb motion of the conductor. Center finger current direction. Center finger current direction. Are you getting? Four-finger flux. Thumb upwards. Center finger. This is the direction of the current. Three fingers are mutually perpendicular. Current direction is current direction. Okay? Current. I am applying from my side. I hope you can understand this. So the direction of the induced EMF is in this direction. This is direction of induced EMF, E or I, current. That is cross. This is cross. Current is going away from the observer, away from the observer. Four-finger flux, thumb motion of the conductor. Current is in this direction. Okay. But some of the students will get confused. See, as for my observation, where the students are doing mistake, listen. They will keep four-finger flux direction, thumb motion of the conductor. They will keep thumb and forefinger properly. But where to keep the center finger, there is a doubt. Where to keep? Remember that forefinger flux, thumb motion of the conductor, but center finger must be always placed along the conductor. The conductor is like this, na? Yes. Your center finger must be along the conductor, because common sense is current will passes inside of the conductor. Na? Current is passes inside of the conductor means your center finger shows current direction means center finger must be always along the conductor. Because center finger shows current, current will go either in this direction or in this direction. There is only two directions, like this or like this. But three fingers are perpendicular. Current is in this direction. Right? Yes. If conductor is moving downwards direction, say current will be in this direction. It will be dot, you can observe. Dot you can observe. Fine? Yeah. Okay. And even the direction of induced EMF can also be found by applying the platform rule. Right hand rule or platform rule. Generally, in the examination, you won't give this big diagram. This big diagram. Generally, how it will be given? See here, this is the flux direction. This is the flux direction. And let me take this as a conductor. This is V and this is B. V and B. How to apply? You are keeping a conductor on the plane. The conductor can be kept like this. If you see from this side, you can feel conductor is like a circle. Then how to keep apply your right hand rule? Four-finger flux direction, thumb motion of the conductor. Current is inwards into the paper. The current is going into the board, into the paper, inwards. Cross. This is cross, no? This is cross. Similarly, this is the direction, say. The conductor, if it is moving downwards, and this is B. Now, how you can apply? Four-finger flux direction, thumb motion of the conductor. Current is upwards. Current is upwards, out of the paper. It's dot. You can feel it is like a dot. This is dot, whereas this is cross. Fine? Yeah. Direction of induced EMF can also be found by applying the right hand platform rule. Another rule. Right hand platform rule, what it indicates? If 4 fingers indicates 4 fingers are placed along the conductor such that flux should enter perpendicular to the palm, thumb shows motion of the conductor. Then 4 fingers indicates direction of induced EMF. Let me write that. The direction of induced EMF can also be found by applying the right hand flat palm rule. The direction of induced EMF. The direction of induced EMF. Induced EMF can also be found. Can also be found by applying right hand flat palm rule. Right hand flat palm rule. Right hand flat palm rule. According to that, statement is like this. Statement is, if the 4 fingers are placed, the 4 fingers are placed along the conductor, such that flux should enter perpendicular to the palm, flux should enter perpendicular to the palm, and thumb shows direction of motion of conductor. Direction of motion of conductor. Then the 4 fingers indicates. Direction of induced EMF. Direction of induced EMF. Okay. The 4 fingers are placed along the conductor. 4 fingers are placed along the conductor such that flux should enter perpendicular to the palm, and thumb shows direction of motion of conductor. Then the 4 fingers indicates direction of induced EMF. 4 fingers indicates direction of induced EMF. Yeah. Again, the statement is clear now? Yes. Now let me explain this. These 4 fingers, right hand flat palm rule. See here. 4 fingers. This is the conductor. 4 fingers are placed along the conductor such that flux enter perpendicular to the palm. This palm should be always opposite to north pole. Flux enter perpendicular to the palm. Thumb shows motion of the conductor. And these 4 fingers indicates direction of induced EMF. 4 fingers. Because fingers are placed along the conductor, they indicate current direction. The fingers which are placed along the conductor, remember that blindly always, you check any right hand rule, left hand rule, car screw, any rule. Fingers which are placed along the conductor indicates current direction. Okay. So lastly, see, 4 fingers are placed along the conductor such that flux enter perpendicular to the palm. Thumb shows motion of the conductor. Then these 4 fingers indicates direction of induced EMF or current. 4 fingers direction of current. If it is moving downwards direction, say current will be in this direction. Okay. Yeah. And even you can find direction of induced EMF. E is equal to V cross B is there. Na? E is equal to V cross B. E is equal to V cross B. V cross B. V to B. This is conductor. This is V. This is B. Now hold the conductor. Hold the very simple way you can apply. Hold the conductor with right hand such that fingers are wrapped from V to B. Fingers are wrapped from V to B. Then thumb indicates current direction, EMF. Hold the conductor with right hand. Fingers are wrapped from V to B. V to B. Then thumb indicates. And this thumb indicates current direction. Current is in this direction. Okay. Yes. Yeah. So these are the very basic things you may be knowing. But I have taken a single conductor. Practical machines, you do not have a conductor, single conductor. It will be in the form of coil. That coil will rotate, na? Coil will rotate. I have taken upwards, downwards. But I am going to take a coil, that coil will rotate. Of course, that coil can be kept in the rotor core. And coil is rotating, then it will cut the flux, EMF will be induced. Okay. So tomorrow I am going to take a coil and with multi-turn coil, then we will come to the practical generator, practical alternator. Okay. So I will stop here, and any doubts are there up to here, you please ask. Okay. Tomorrow your schedule will be, tomorrow class is same. Tomorrow class 5:30 to around 9. Okay. I will see the time, 9:30, how much you are saying 4 hours means. So I can start only at 5:30, not before that. 5:30 to 9 or 9:30. Mostly 9. Mostly 9, because 9:30 means lunch time, dinner. You need to go for dinner. Na? Okay. Anyhow, on Sundays, I will take extra maximum. On Sundays, definitely we will have some more time in the morning time instead of having 5 to 9. So we will cover, nothing to worry. Right? So tomorrow schedule is, let me write, tomorrow schedule is also same. (5:30 to 9). Okay. Yes. Yeah. Now tell me any doubts are there. You please ask. I will read out your doubts. Okay. Cross means current is entering or leaving. Cross means inside. Current entering. Current into the paper. Current is into the paper. Yeah. Yes. Is synchronous machine is too lengthy part, sir? Okay. Too lengthy in the sense, for in machines, transformers and synchronous machines, big topics. Transformer and synchronous machines are big topic. Okay. You please raise hand now. So just a minute. You can ask. I will give the option. Hand raise. Just a minute. Please stay there. I will ask. I will give the permission to hand raise. Okay. Pallavi. Yeah, you can ask your doubts. So others also can. Pallavi, are you there? No. You unmute and you can ask. Bharat, are you there, Bharat?
Yes, sir.
Yeah, tell me your doubt.
So my doubt is, sir, for low frequency operation, you said that we need a large size of machine size has to be bigger.
Yes, 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 yes.
So why is it so, sir?
For large, for us, low frequency, see, induced EMF is equal to 4.44 kp kd 5ft, no, generated EMF equation. You may be knowing this.
Yes.
We are also going to see 4.44 kp kd 5ft. I want some 1000 volts, say. For example, I want some 1000 volts. For 1000 volts, frequency is less. For example, frequency is very less. When frequency is less means, in this, what should be the number of turns? Kp kd, it is nowhere related with the frequency. Kp kd flux constant, say.
Number of turns.
Frequency is less, more number of turns are required. Na?
Okay.
When more number of turns means definitely more slots are required. When more slots means stator size increases, rotor size increases, because power is proportional to induced EMF for a given rating. That's the reason. For example, you want 100 kilowatt alternator, say, with low frequency, more turns are required. This is same for every motor or whatever it may be. At low frequency, high, more number of turns, size is more. Okay?
Okay.
Yeah. Fine. Next, Pallavi, Ram Sharan. I'm unmuting all the people. Those who want, you can ask.
Hello, good evening, sir.
Good evening.
Sir, the concept behind that asynchronous generator. Sir, here we can say that EF is 0 for that asynchronous generator.
Yeah.
Synchronous generator, asynchronous EF is equals to 0. Then how we can define that current is leading in nature, and that will be it will be leading reactive power will be absorbed.
Yes, it is leading only, leading. Yes. You want reason how it is leading?
Means the direction how it will flow. So according to current direction, I want to know.
Current direction, AC current. It will absorb the reactive power. It operated leading power factor. I didn't get your question.
Actually, for motor it is lagging, and
yes.
For a generator, how we can say it, means how you can define it.
Inductor operation, capacitor operation. See, under excited generator, how it act as? Under excited motor, say for example, induction motor is said to be no excitation. No excitation. No excitation, it is operating at lagging power factor. Lagging power factor means it is taking the reactive power. Current convention. It is taking the current. Yes. Current means how it acts as inductor. Lagging power factor means inductor. Inductor always absorb the lagging reactive power. Okay. Yes. Generator, when you are taking generator, you have to take a upwards direction always. Current will be giving. It is delivering. Say. But when induction generator, it is absorbing the leading reactive power, means it is acting like a, right? It is also said to be acting as an inductor. It is also absorbing inductor. Right. Under excited machine, generator or motor, they will absorb the reactive power. Over excited, they will deliver fine. But induction generator, induction machine, there is no excitation. That's the reason they will absorb always. For example, magnet is there. Magnet is there means for synchronous machine, I will give field side. Okay. You are creating a magnetic field. But induction motor, induction generator, you are not giving. It will take it.
Yes.
See, I understood your question. At the end, I am going to write a table. Under excited, only one table, one point that you need to explain about it with respect to inductor and capacitor operation. Inductor and capacitor, right? I am going to give that under excited synchronous machine act as inductor. Generator or motor, both will be act as inductor. Over excited synchronous machine act as a capacitor, motor and also generator. So
Okay,
like induction machine is under excited. So both will act as inductors only, generator and motor. Of course, one is acting as a lagging power factor, another is acting as leading power factor. Current conventions you have to take. Motor, you have to take current is said to be inwards. Generator current will be always upwards.
outward.
Yeah. At that time, this doubt is going to be cleared very clearly in the chapter of seventh chapter. Seventh chapter, I am going to write all these things. At that time, you cannot raise this doubt at all. If I explain, say, now if I explain, you can't understand also. I have given already. Over-excited generator or motor. Right?
Yes.
That act as a capacitor.
Sir, another small doubt is.
This is general statement you take now. This is you are going to realize it. I will draw the phasor diagram and at that time you can find. I will compare with synchronous generator, induction generator. That's what I told in the beginning. That's what I told in the beginning. How induction generator operated leading power factor means you have to wait until that point.
Yes. Sir.
Yeah. Next. Okay. Right.
Sir, doubt is, sir, that North Pole, South Pole, when you are moving in a horizontal direction, we can the conductor will face same flux.
Yes.
Yes, but in the transverse direction also it is facing same, because for that particularly for that distance only it will be move up and down, means that phase will be same flux, na?
Flux linkages point of view, I am not talking about flux link. Flux linkages will be valid for a coil. If you take, then you can realize.
Okay.
When you are taking coil, conductor, you cannot visualize flux linkages. That's the reason I am using a word cutting.
Cutting, okay.
Rate of change of flux linkages or flux linkages you can visualize with a coil. Instead of taking a conductor, if you take a coil, then you can understand.
Yes. Okay, sir.
Coil is clear. When coil is rotating, then you can visualize easily. Conductor means you cannot visualize. That reason for a simple conductor, I never use flux linkages.
Okay, means it will be caught in the transverse direction.
Cut. I am going to make it simple words. Rate of change of flux linkages is nothing but cutting, I will say. That's all. Cutting you can easily understand. But rate of change of flux linkage means that will be out of our mind. You cannot visualize. That's the reason cutting simple.
Yes.
If cutting is more, EMF is more. I am going to make some simple terminology. And just by looking at the diagram and you can able to say answer. The terminology, instead of changing rate of change of flux linkages, simply I will say cutting. Cutting maximum, EMF maximum, that's all. Okay?
Okay.
Yeah.
Thank you, sir.
Yeah. Next.
Hello, sir.
Yeah. Sai Charan.
Sir, one and only doubt, sir, that when the flux passes through between that coil, it will induce, or if the coil cuts the flux, it will induce EMF, sir. Sir, you told two explanations, sir. No, sir.
Yes.
For that only, I'm asking, sir. You told two different explanations.
This one, na?
Yeah, sir, in that, yes, sir, this one.
Yeah,
right side, sir.
Yeah.
In this right side one, you took a coil of two conductors, and in that
coil is rotating. I am rotating.
Yes, sir. You told that when the maximum flux is passing through between that coil, then the flux inducer is EMF inducer is maximum. You told us, sir.
Not maximum, zero.
Okay.
See here, this is can you able to identify? This is coil. If all flux lines are passes inside of the coil, then linkage is maximum. But linkage is maximum, is it cutting any flux lines? No, it won't cut. Right?
Yes, sir. Yes, sir. Understood, sir.
That again we are going to see flux linkages. I will take at the time of EMF equation a coil. But what I mean to say is only here the thing is you need to understand when coil is not moving. For example, here all flux lines are passing, right?
Yes, sir.
But if you not rotate, do not rotate, what is going to be happen? At t is equal to 0 also flux linkage maximum, t is equal to after 1 milliseconds also maximum, 2 milliseconds also maximum, because coil is I am not rotating. Is there any change in flux linkages? No change.
No change.
Always it is 10 only passing, therefore no induced EMF if coil is stationary. But while you are rotating, what is going to be happen? At this instant flux linkages maximum, and all 10 milliwebers are passing. When rotating, position of the coil is changing, the position of the coil changes. Some flux lines will pass inside, some is going outside of the coil. That is what we want. Change will come. When coil is rotating, position of the coil changes. Not always all flux lines are passes. One instant 10 milliwebers are passing. After some time some 9 milliwebers are passing. After some time some 8 milliwebers. After at sometimes it is 0. It will changes for 90 degrees rotation. Flux linkages 100% changes.
Okay, sir. Understood. Yes. Sir.
Okay, right.
Hello, good
Next,
evening, sir.
good evening. I am unmuting. Okay, tell me.
Sir, I have a doubt that there are different generating voltages like 6.6, 11, and 33, no, sir?
Yes.
Means what is the reason that we say that modern countries use 33 kV and we use 11 kV? Means after all, we can step up the voltage and gain the same voltage, no, sir? What is the advantage, sir?
Generation level, it is based on the generating station. Generating station means what is the rating of your alternator and what is the speed that is available, head is available.
Yes, sir.
Right? You can have 11 kV generation also, 22 kV, maximum 33 kV also.
Right, sir. Is there any advantage, sir? 33 kV have over 11 kV?
Definitely at high voltage generation levels, whatever the voltage is having, there is not because of only advantages. What is availability?
Okay.
For example,
Availability.
there your generating station.
Yes.
What is the rating of your generating station? Number one. Okay.
Yes.
For example, steam pressure, how much it is available. It is only depends on the designer. There is no particular advantages with respect to 11 kV, 22 kV. But transmission level, coming to the transmission, your voltage must be high.
Yes, sir. Yes, sir. We
That
step up
you
that.
can step up.
Yes, sir.
If otherwise, all their 33 kV generation means all they not necessary to go. Remaining things also is a matter. For example, my alternator rating is less means definitely voltage rating also will be less.
Yes, sir. Correct.
If I am going some 500 MVA alternator, definitely I will go for higher voltages.
Yes, sir. Right.
Higher voltages rating. And conductor size also it is depends upon what is your current rating. It's all depends upon only design.
Yes, sir. Correct.
It is not compulsory for 33 kV, 22 kV. It is
Thank you.
interest of. Okay, right. Next. Anyone you can unmute and you can ask.
Hello, sir.
Hello. Yeah, tell me.
Hello, sir. Sir,
Yeah.
what is the difference between generator and alternators?
No generator, ma. Generator, synchronous generator is generally called as alternator. Alternator means it is generating alternating voltage, alternating current. And your doubt may be, I can also call induction generator also as alternator. That is your doubt, na?
Yes, sir. Actually, yeah, recently I got that question, sir. What is the difference between generator and alternator in interview type questions?
Generator can be any generator. AC generator means either induction generator also you can call AC generator, and synchronous generator also you can call AC generator. Reluctance generator also you can call AC generator. But synchronous generator is called alternator. Alternator means it is generating alternate voltage, alternating current. Even induction generator also will generate alternating voltage, alternating current. And there you may say, sir, it is also generating alternate voltage. Why can't we call alternator? It is also alternating. It's generally called as, generally, there is no particular specific reason, namely called as alternator. It is synchronous generator means always rotated synchronous speed.
Okay, sir.
They are referred as alternator. There is no some other specific reason. This is generating only AC, I can call alternator. No. AC generator. I can say synchronous generator also AC generator. Correct. That only I can call alternator, but induction generator, AC generator, it cannot be called as alternator.
Okay, sir.
Ah.
Sir, in this page, sir, when the flux, I have two doubts, sir.
Ah.
Whether it is the flux linkage EMF induced is maximum
Ah.
or maximum number of flux lines going, then that EMF is maximum, sir.
When all flux lines are passes, right? Flux linkage is maximum, but rate of change of flux linkage is minimum. Induced EMF will be minimum. Right now, you don't worry about this flux linkage maximum. I am going to take EMF equation, derivation of EMF equation. I will take very clearly. I will draw one coil. I will draw the isometric view. See the conclusions what I am going to get. If all flux lines are passes inside of the coil, no cutting of the flux. Induced EMF will be 0. When flux linkage is maximum means induced EMF is minimum 0. Vice versa. If flux linkage is minimum, induced EMF will be maximum.
I didn't get that, sir. When the flux lines are going, maximum flux lines are going means we will get the EMF induced is maximum.
No. Induced EMF is proportional to rate of change of flux linkages. Induced EMF is proportional to what? d psi by dt. Induced EMF is proportional to cutting, d psi by dt cutting. If all flux lines are passing inside of the coil, if they are not cutting, what is the use of that? Can you able to see my are you video? Can you able to see? Yes, please.
Yes, sir. Yes, sir.
See, this is North Pole, ma. This is South Pole. North Pole, South Pole. All flux lines are passing.
Okay.
Passing. But at this instant, how this coil sides can move? They will move parallel to the flux lines.
Yes, sir.
This is the coil. This is my hand is a coil, na? Coil. This side one conductor. This is moving like this. This is moving like this, right? Or else you see, I hope you can visualize. This is one conductor. This is another conductor. Pole is here. But all flux lines are passing inside of the coil. But whenever conductor at that position, tangential position, how it will move parallel to the flux lines. Parallel. No cutting. Though all flux lines are passing inside of the coil, they are not cutting. EMF 0. But when coil is rotating like this, say, when coil is here, pole is here. This is the pole, say. For example, this is the pole. This is the pole. This is the pole. Right? And another pole is like this side. This side. Okay? And when coil is under the pole, coil is earlier like this, but now coil rotated. When conductors are exactly center of the pole, all flux lines are passes outside of the coil. All flux lines. Now see. This is the coil. Earlier, all flux lines are passing inside of the coil. But when conductor is moving, this conductor will move like this conductor will move. They are moving tangentially perpendicular. No cutting. But when coil is rotated by 90 degrees, pole is here. This is the pole. Conductor is here. This is one conductor, this is another conductor. When they are moving, how they will move? Perpendicular to the flux lines. Maximum flux cutting. That is called rate of change of flux linkages. We are going to call. Okay. At the time of EMF equation derivation, I will draw the diagram. Two diagram I will draw. Finally, I am going to make a single conclusion. When coil is under the pole, EMF maximum. Coil is along the direct axis, EMF is maximum, I will say. I will make general statement to avoid all the confusion. With the diagram, with the little explanation, I will write a simple conclusion that will be fixed in your mind. You never forget. Okay? And yeah. If I want to explain means it will take its own time. That is EMF equation derivation is 40 minutes time. So if I draw the diagram only, you can understand. Because online, you can't able to. That is also visualization also difficult, na? Yes. But
yes, sir. I am not able to.
I need to draw the diagram. Don't worry now. At the time of EMF equation, you are going to get it. Okay? So next class or next page number
15, sir.
Page number 30, na?
No, sir. 15.
1.5. Okay.
Same doubt only, sir. Here, when the flux is maximum, EMF you draw from zero, no, sir. That's how you got it.
Yeah. d psi by dt. EMF is proportional to d psi by dt is different. D psi is different.
Okay.
That you are going to now you in this diagram only you have to understand. Forget about rate of change of flux linkages or this diagram. This you leave it. Okay. Important thing is what you understand. When if coil is rotating, then only flux linkages changes, na?
Yes, sir.
That point enough. If coil is not rotating, flux linkage is constant.
Yes, sir.
Flux linkage is constant. Ante at t is equal to 0 constant, t is equal to 2 milliseconds constant, t is equal to 10 milliseconds constant, or tomorrow also constant, after 1 week also same.
Yes, sir.
Will be there any induced EMF? No induced EMF.
No.
But when coil is rotating, what happened? Flux passing inside of the coil changes, instant to instant changes. Why? Because position of plane of the coil is changing, na? Plane of the coil is changing. So flux lines passing inside of the coil changes, then induced EMF takes place. That you
But in left,
you just have idea about that point, that is enough. But when linkage is maximum, induced EMF is minimum, that point we are going to make it very clear at the time of EMF equation.
in the left side diagram, it is just normal, no, sir. Flux is maximum, EMF.
Flux is a flux in the transformer. I am giving AC, kada? AC. AC
Yes, sir.
means flux passing through the coil is constant or changes.
Flux passing through the coil changes.
Why changes? Correct, you are correct. Why changes?
AC nature, no? It is.
That's what. Coil is not moving. Okay. But flux passing inside of the coil, time varying nature. With the gravity changes. Therefore, flux linkages is changing. That is what it is required. EMF induced.
Okay, sir.
Ante, in two diagram, what I want to explain is first one statically induced EMF. We are giving AC current. Therefore, flux is time varying nature. No relative motion is required. Flux passing inside of the coil changes, instant to instant changes. Therefore, induced EMF takes place. The change of flux linkage we are getting in the first diagram. Without any rotation, it is by nature time varying flux. But second case, right?
It is not.
If the same thing, for example, what I told for first diagram only, if you give DC, what will happen? First diagram, DC you give, what will happen? Flux constant.
Yes, sir.
Flux constant. Same constant flux only passing inside of the coil.
Yes, sir.
Can you get any induced EMF?
No, sir. Because of constant.
No change, because it is constant, no change, no induced EMF.
Yes, sir.
That same thing what I want to explain is, if I give DC, right?
Yes, sir.
Rotation takes place. Transformer, first diagram, what I am saying, if DC given, coil is not rotating, therefore always same flux is passing, that's the reason no induced EMF.
Yes, sir.
But I want to give DC, I want to induce EMF means then coil has to rotate. If DC is given, coil has to rotate. That is what I am taking in the right diagram.
Right, right.
For coil to rotate, what to do? You have to cut that portion. You have to
Yes.
put some air gap. Na?
Ah.
So I am cutting that flux, I am rotating, and now I am giving DC. When coil is rotated, then flux passing inside of the coil changes. Therefore, EMF I am getting. That is what dynamical induced EMF. So dynamical induced EMF require relative motion with constant flux. Statical induced EMF, no relative motion is required, but time varying flux is required. That is what I explained.
Okay.
Okay.
Okay. Thank you, sir.
Yes, fine. Next. Hello.
Hello, sir.
Yeah, tell me.
Sir, as per the Lenz law statement, you are told that the EMF opposes the cause behind its production.
EMF in the sense EMF, where EMF is there, current will be there, na? Path is closed.
Yes, sir. Sir, as per the sir, will you please explain the Lenz law diagrammatically, sir, once how it opposes actually?
See, this is the magnet, no? When
Yes.
if I am pushing the magnet inside of this toroid,
Yes.
Of course, coil has kept on the toroid. When you are moving from left to right, this is a coil. When you are moving left to right, flux is increases, na? Inside of the coil, flux increasing. And which direction flux is changing? You are keeping here. Center more flux linkages. If you insert the entire magnet,
అదంతగానం ఉండే ఎక్కడ ముంచిండ్రా దాన్ని తిన్నదా అంతగానం ఎందుకు తింటారు
one of your friends. Are you getting? Hello.
Yes, sir.
Sai Charan. When we are moving, flux is passing. When magnet I am moving inside of the coil, flux linkage is more. And the d phi is in this direction. D phi is left to right because it is moving left to right. Sorry, right to left. Flux linkages d phi. This is the d phi changing.
Yes, sir.
Right? But induced flux, according to Lenz's law, EMF will be there. When you are moving magnet, flux instant to instant changes because magnet is moving more inside, therefore more flux. Flux
Yes.
changes instant to instant, therefore EMF is induced. Na? Yes.
Yes.
When induced EMF, it will drive the current as I have closed the
నిద్ర లేదంటే ఇంకా ఇప్పుడు నీకు ఈ నిద్రకు అలవాటు కానీ ఇంకొక 10 రోజులు 15 రోజులు అట్లా పడుతుంది అప్పుడు ఇంకా అప్పటి నుంచి మళ్ళీ నిద్ర పడుతుంది
drive the current. But
అప్పటి నుంచి
the
11
current
గంటలకు అట్లా
also produces the flux in which direction? Opposite direction, that of d phi. D phi induced EMF must be opposite. Okay, opposite means in the coil current direction, which direction it should be? Apply your thumb rule. Thumb rule. Whatever I have given, thumb rule is correct or not? This should be the current direction. Then only your induced flux will be opposite to the d phi.
Yes.
Is it clear, Charan? Right? First d phi is there. And d phi induced must be opposite means apply your thumb rule.
Yes, sir.
That's what. Current direction must be in this direction. Then only it will induce the flux in this direction. And when current is means, I can say induced EMF will be this is plus minus, this is polarities. So current must be in this direction. That will give the Lenz's law.
Okay.
Okay. Right.
Good evening, sir.
Good evening.
The large effect of harmonics which you explained in problems with high frequency generation. Can you explain it?
Large frequency, no?
Large, no, sir. Yes, high frequency generation. Large effect of harmonics.
Yeah, definitely. When frequency is more, the harmonic frequency n times of fundamental, no?
Yes.
For example, 1 kilohertz your fundamental frequency.
Yes.
Okay. 1 kilohertz means fifth harmonic frequency 5 kilohertz. And that effect will be on the rotating machines. They will create the vibrations. No? They will create the vibrations. And of course, they are also create their own losses. Harmonic losses also. Harmonic more frequency means more. Third, fifth harmonic also will produce their own flux. Vibrations are more. Effect of harmonics are more. No?
And so in the first point, which you explained with high frequency, the reactance of transmission line is large and
Yes.
power transmitting capability of transmission line will reduce. If the load is capacitive load, so can we use high frequency generation there? Will it be useful there?
These may be capacitive load, whatever. Loads are generally are using capacitive loads. Where are you using?
No.
Inductive
Inductive
loads
load.
only. Yeah, transmission line is inductive nature mostly.
Yes.
That is practical cases. And capacitive loads we never use, no? Very rare.
And sir, reactive power, can you explain how reactive power stabilizes voltage?
Yeah. That now if I explain you cannot understand. That will be in the 6th chapter. 6th chapter, 7th chapter is totally reactive power. At least you might have heard about in transmission line,
Yes.
voltage stability. When voltage stability, you will get reactive power. Sufficient reactive power must be available in the power system.
So what is the use of reactive power?
But reactive power only reactive power is called magnetizing power.
Magnetizing.
For example, your stator core is magnet, no? Induction motor
Yes,
is
sir.
there. Stator core
Yes.
is magnet. right? But for power conversion, magnetic field is essential. Magnetic field is the medium through which power conversion takes place. Okay, who is creating that field? Reactive power is creating. Okay, but in our alternator, who is creating the magnetic field? DC excitation.
DC excitation.
So if I give normal excitation, sufficient DC excitation, no need of any reactive power. But I can over excite it so that it will deliver the reactive power. If alternator also under excited, it will also absorb. But practically we will design for over excitation. Okay.
And sir, is there a reason for using only 2 poles, or it is a convention or something?
Sorry?
You said that 2 poles are required, are generally used, and we have calculated 3600 RPM.
Steam power station generally 2, minimum 2, maximum 4. Maximum 4 only. Steam power stations. Hydro power station you can have 20 poles, 30 poles. Why? Because 2 poles means around 3000, 3600 RPM. Its efficiency, turbine efficiency is better.
Okay. That's why for better efficiency.
Better efficiency.
Okay. Thank you.
Okay, great.
Hello, sir.
Hello, yeah, tell me, ma.
Sir, can we use the same machine as motor and generator, sir, just by
Yes.
changing input?
Exactly. Synchronous generator can be used as synchronous motor.
Okay, sir. Sir, another one more doubt, sir.
Construction all at the time. Machine same. Yeah.
Okay, sir.
Yes.
Sir, you said no, sir, right hand flat palm. Can you
Ah.
open that slide, sir? 17, slide number 17.
Tell me.
Sir, here, when velocity is downward direction, how to apply that tool, sir?
Okay. Can you able to see my video?
Yes, sir.
See. This is conductor, na? North pole is here, south pole is here. Conductor is this. I am keeping this direction, thumb upwards, na? Flux direction upwards. Therefore, this is the current direction. Now, if it is moving downwards, say, how I can keep like this? Fingers are placed along the conductor, but thumb downwards. But your palm should be, flux should enter at perpendicular to the palm. This palm should be always opposite to North Pole. Either you keep like this or keep like this. Flux should enter here. So now this is the conductor. My four fingers are keeping along the conductor such that flux enter perpendicular North Pole, flux thumb is downwards. So therefore, this is the current direction. Current will come towards me. Current you will get like this. Current you will get like this. In this way. It is dot.
Okay, sir.
Correct? Vaishnavi.
Okay, sir. Sir,
Yeah.
this one also, sir, you said again one more method. No, sir, we have to rotate V in the direction of B. no, sir.
V2B. V2B.
V2.
Yes.
I'm not getting this this one only, sir. Downward velocity, how to rotate it? It should be up, no, sir. Resultant EM.
Okay. Yes. See here. In this diagram, V2B. Here it is V2B. V2B only. I am keeping like this. Perpendicular, vertical. You take conductor vertically. My paper is there, na? Board.
Yes, sir.
Okay. Or from the same diagram you want to explain. The first diagram, whatever I have drawn, na? Yes. Say, for example, this conductor downwards, na? Downwards. Listen. Downwards means keep like this. V2B. It has to be V2B means which direction it will come? Current is coming in this direction. Earlier, are you getting? V2B, thumb is in this direction, thumb in this. But if you are keeping like this, V2B means current will come this side. This is V2B. V downwards. V is downwards. So therefore, V2B. Fingers must be wrapped like this one. Are you getting my point? Hello?
Yes, sir. I am listening.
Fingers ikkada undi. You start from here onwards. V2B. This is the direction.
Outwards.
But if you start here, V is
This
here,
one.
V is here, downwards. like this. V is here, V to B, V to B. Counterclockwise direction, na, when V is here, you see
Yes.
in this diagram. In this diagram, you see. Are you getting this diagram? I am explaining.
Yes, sir.
This diagram you explain. V to B means which direction your fingers must be wrapped clockwise.
Clockwise.
But here V to B counterclockwise. The fingers you have to keep counterclockwise.
Okay, sir.
Then you
Just
get-
like curl, right? Curl.
curl only. Curl only. That is what.
Yes. Okay, sir. I got it.
Okay. No?
Thank you, sir.
Yes. Okay. Okay. Right. Next, anyone? Hello? 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 Yes, I'm closing the session.
Sir, your contact number,
Hello?
sir, your contact number and details.
Yeah. I will give tomorrow.
Okay, sir. Okay, thank you. Good night.
Right.
Hello, sir.
Hello?
Sir, just a general doubt, sir. Like for the new batches, we did not get any machines classes. So will that affect this?
And the new batches is not started at all.
No, sir. Did not get any machines related class.
Oh, earlier machines topics is never been. No, it's not started for you.
Yes, sir.
No other machine topic is started. Not yet.
Yes,
no?
sir. Yes.
This is the first. This is the first class, huh?
Yes, sir.
For machine spot. No problem. Nothing will affect it because we will take even physical classes also. Synchronous machine started for one batch first, and some other batch DC machine will be started first. Like this parallelly we will start because students are at least they might be completed. They are joining for GATE examination in the third year level, say. Hoping that most of the third year level. Third year level means already they might be completed their DC machines. That general knowledge is enough. Or
Okay.
zero knowledge also, nothing to worry.
Okay, sir. Okay, sir. Thank you, sir.
Yeah. Most of the times I only start, even physical classes also, I will start with synchronous machines. Once synchronous machines are completed, say, DC machines, other things are very simple. Only thing is, the right hand rule, left hand rules are very common to all the machines. From later onwards, they are not totally, they are totally synchronous machines, totally different from the other machines. So
Okay, sir.
they won't affect you, nothing to worry.
Okay, sir.
Yes.
Okay, sir. Thank you, sir.
Right. Okay. So I will stop here.